Good evening. Can you hear me?
Good
Yes,
evening,
ma'am. Good
ma'am.
evening.
Good
Yes,
evening, ma'am.
ma'am.
Good evening, ma'am. Good
Okay.
evening, ma'am.
Evening, ma'am.
Good evening, ma'am.
So all set for the quiz.
Yeah, ma'am.
No, ma'am.
Okay. So we will do a quick revision and spend some time on doubts so that if there is any doubt that you have, it will all be clarified.
I have one doubt.
Yeah. You want to start with doubts right away, or we
Yes,
can
ma'am.
discuss?
Doubts right away.
Ma'am, we can
Okay.
start with a
Ma'am,
mock
we can
test.
start with the test for all the concept first, and then doubts can be asked.
First you do your part, ma'am. Then we can
Yes,
do.
yes, that would be better. You can do your part, and
Yeah,
then we
we'll
can
do a
ask the
very
doubts.
quick recap so that we will
Yeah.
not spend time. We
Yeah.
won't spend a lot of time on concepts
Hmm.
because it has already been covered in detail in the live
Uh,
sessions earlier. So we will do a very quick recap and then we'll
Yeah.
take
Ma'am,
doubts.
I have a doubt regarding one concept.
Yes, which one?
Regarding the dimension of a vector space.
Yeah, we'll do that. We'll
Okay.
cover that. Yeah. Okay. So
Ma'am, will
yes.
this doubt the revision be similar to the one in maths one only, or like the
Uh,
revision that we had in maths one? They told the weightage of the marks, like
No,
kind of.
see, with respect to weightage, let me make it clear. Every topic is important and the weightage is equal, I'd say, because you cannot solve a system of linear equations without knowing what vectors are or matrices are or determinants are. So every topic is interlinked, kind of. So the weightage, we cannot tell some topic has more weightage for this reason because every topic is interlinked. So the weightage is equal, means all topics will have equal weightage. That's what we'd like to
And
say.
would you be telling us something important for the quiz?
So
Exactly.
you already have the mock paper, right? The
Yes,
quiz
ma'am.
will be similar to the mock paper.
The quiz should
Ma'am,
be
the
similar
pattern of
questions.
questions answering them will be also the same or different, ma'am, like the graded assignment.
So the mock is like something what you're going to see in the quiz. That's
Ma'am, what will be the
so,
duration?
Oh,
Duration of the quiz.
Thank you very much, ma'am.
yeah. The quiz may be a little easier than mock, but the mock is the pattern. That
Ma'am,
is
what will
what
be
is
the
your.
duration of the quiz?
Ma'am, level of difficulty will be less.
It'll be more or less like the mock.
Ma'am, duration.
It's not going to be more difficult than the mock.
Where is the mock solution?
In solution release.
Mock solutions are not on the portal.
No, they are not.
Ma'am, what will be the duration of the quiz?
1 hour, right? The exam is for 1 hour. Means the math. If you are writing combined courses, then you might have different timings. But for math, it's the exam as such is for 1 hour.
Yes, ma'am.
Another thing, we used to get some really like similar questions in the revision session itself. Will we get that in maths too also, like in this session?
We'll do the mock paper. We can discuss mock paper. I'm telling you, the paper will be similar to the mock paper.
Okay.
Ma'am, when will the mock paper solutions ka PDF come?
Yeah, just a second. I'll ask. Why?
Mock is actually the previous year's papers, no?
No. We prepare a separate mock, which is similar to the quiz paper.
Okay.
Okay, so
The quiz will be more or less in the similar pattern of mock or how?
yes, you can take the mock as an actual mock for the quiz. So that's the mock is going to tell you how the quiz is going to be. It will be more or less like the mock.
Okay.
Ma'am, like those questions were where we had to enter the option number. That was a little scary because if one option we miss, then the question goes wrong.
Yeah, so you
Like-
should be careful about that. Yeah.
Like the MSQ type is a little better from that point of view. We select the option which is most correct and we leave out the others.
Hmm.
And the question weightage also, week wise weightage also will be similar like mock.
Yes, ma'am. That's a request because actually,
What do you think? Is
a
mock
question.
skewed?
Sorry?
The mock is the mock skewed towards any week, or you think it is?
No, ma'am. It was
equally distributed?
balanced.
Oh,
It was
it's
balanced.
Yeah, it's going to be like that only.
Ma'am, what would be the number of questions we can expect?
Again, it's more or less similar to the number of questions in mock. It's
Okay.
like we prepare the mock paper based on the quiz paper, so it's going to be like you can expect a plus or minus 10% change. That's it.
Okay.
Nice.
So there are 14 here, maybe around 10 to 15 questions maximum. It's 1 hour paper, no, so it won't be that.
Can we start with the concept?
Yeah, we will do that. Yeah, that will be better. We'll do a quick recap of the concepts and then.
And ma'am, before that, any update on the solutions? No.
Yeah, I've asked. Once they reply, I will let.
Okay. Thank you.
So you want the
one
solution,
general
right?
question actually. The mark is mentioned as graded.
Yes, ma'am.
Will it have any weightage? Because
no, I think because it was a timed mock.
So mock doesn't have any weightage.
No, in the top, if you see, there is mentioning as for grading.
No, it's not graded. I think it's because it was a timed mock.
Oh
yes.
It is only for practice.
Yes, ma'am. It is for practice, but
it will be not graded.
But
Yeah,
it helps
this is only for
it
practice.
helps in improving the grade, as the bonus marks are awarded for attempting more tests. And if you get more than 40%, then
let's
you
not
get bonus
discuss
marks.
all this stuff into this session. This is more of a topic is specific.
Okay. We will start. We'll
stick to that.
Yeah.
Let's start the session.
Yeah. So in week 1, we started off with vectors, right? Vectors in general in R2 and R3, we discussed what vectors are. So why these were called vectors was already made clear. Now that you know vector spaces, these two are vector spaces with respect to usual addition and scalar multiplication. So the elements of R2 and R3 were called vectors, right? Yeah. So any element in R2 will have 2 components, and how do we add them?
Component wise.
Yeah. So the component wise addition is called the usual addition. This is the usual addition which is done component wise. Similarly, when we have elements in R3, it's 3 components. So we'll have 3 components, and again it's component wise addition. So this is the usual addition in R2 and R3. And for a vector space, we want an addition and a scalar multiplication. So how is scalar multiplication defined in R2?
Again,
component wise, right?
Again, component wise multiplication.
Yeah. So this is the usual scalar multiplication in R2 and R3. So using this addition and this scalar multiplication, R2 forms a vector space, and hence its elements are called vectors. And using this addition and this scalar multiplication, R3 forms a vector space. So yeah. So we know how to add vectors, how to do scalar multiplication of vectors, and using this concept, we saw how to add 2 matrices and do scalar multiplication on matrices. So when can we add 2 matrices?
Quick question here. I have a noob question. Can we add a vector from R2 to a vector from R3? Is that possible or not?
Why don't you tell me whether it's possible or not?
I don't think so. It is possible. Just confirming it.
Yeah, it's not possible because you'll be missing out on one component, right? That means you're doing it component wise. So x1 y1 plus x1 y1 z1 will not make sense because there's no third component here to add it with z1, right?
Okay, I just wanted to confirm because wherever I saw it was like that only. I thought, can we put 0 z1 and add?
See, x comma y comma 0 is an element in R3. This is not an element in R2. When you have a 0 component,
when a component is not given, you cannot assume it.
Yeah, the number
not
of
given
components
means it does not exist.
Yeah.
Only for scalar multiplication we can take this 0.
No. For scale, what do you mean by scalar multiplication? We
Means
can
in
take 0?
linear equation, if one thing is not there, 0.
Oh, yeah. If a variable is missing,
The variable is missing. Yeah. I mean to say that.
Yeah. Okay. So how do we add two matrices, and when can we add two matrices?
Matrices can only be added if they are of same size.
The dimension.
Yeah.
Same order.
Yeah. So they should be of the same order, and the order is in the order of number of rows first, and then number of columns. And again, addition is component wise, because you can treat every row of a matrix as a vector or every column as a vector. So since we add vectors component wise, you can add two matrices component wise. And similarly, we can also define scalar multiplication of a matrix. Again, since scalar multiplication of vectors is component wise, scalar multiplication of matrices is again every entry of the matrix gets multiplied by the scalar. Okay. So how do we multiply two matrices, and when is multiplication possible?
When the number of rows of the first matrix is equal to number of columns of the second matrix.
Number of the first matrix is equal to the number
Column
of rows
of
of the
first
second.
into row of the second. Yes. Column of first.
So the number of columns of the first matrix should be equal to the number of rows of the second matrix. These two should be equal, and the order of the resultant matrix AB is going to be M cross P. Yeah. So this is going to be of order M cross P. The number of columns of the first one should be equal to the number of rows of the second one. And how do we multiply? How is matrix multiplication defined?
Ma'am, first row into first column of the both the respective matrix will result into the first element of the resultant matrix.
Yeah. So suppose I have a 1 cross 3 matrix and a 3 cross 1 matrix. I'm allowed to multiply, and the product is going to be a 1 cross 1 matrix. How you do it is you do it entry wise. A1 B1 plus A2 B2 plus A3 B3. So what you do here is you take the first row of this matrix and multiply it, each element of the first row with the corresponding elements of the first column here, and then you add the products. This is how you do matrix multiplication. And if you have more number of rows and columns, you do this to get every entry of the product matrix, right? So is there any doubt in how to multiply matrices?
No, ma'am.
Okay, fine. So then after we defined multiplication of matrices, we went into the concept of determinant, right? How will you define the determinant of a 2 cross 2 matrix?
The concept was of linear equation, I guess.
Diagonal.
Diagonal multiplication.
AD minus BC.
AD minus
BC. Yeah. So when you have a 2 cross 2 matrix, you find the determinant by doing AD minus BC. So any higher order determinant, if you want to find the determinant of any higher order matrix, what you try to do is you try to split it into smaller pieces such till you reach a 2 cross 2 matrix, and then you know how to find the determinant. So determinant is possible only for n cross n matrices, right? Only for square matrices. Yeah. So how will you find the determinant of FGHI? How will you find the determinant of a 3 cross 3 matrix?
First, we will assign the sign convention like plus minus plus
element and eliminate the
then
row
we
and
will take
column.
the first element and then we will take the determinant like cofactor wise.
So you can expand it along any row or any column. What you do is, suppose you're expanding it along any row, then it's going to be AI1 CI1 plus AI2 CI2 plus AI3 CI3. What is this? I've expanded along the ith row here, right? So suppose we are expanding it along the first row, it's going to be this. What is Cij?
Cofactor.
Yeah. The cofactor of Aij. And how do I get the cofactor?
Minus 1
to the power of
I
plus
1
or
to m minor.
Yeah, minor of Aij. And how will I calculate the minor of Aij?
M, it is the
Eliminate ith row and jth column.
Yeah, and then remaining we take
we
the
want to
determinant of that remaining.
eliminate the row and column.
Yeah. So you eliminate the ith row and the jth column. That is the row and column in which this element appears. And then you calculate the determinant of the remaining submatrix. That's how you calculate the minor of an element. And once we know the minor, we know how to calculate the cofactor. And once we know the cofactor, we can calculate the determinant of a matrix, right?
Sir, ma'am, can you please repeat? I understood cofactor, but the minor is I cannot get.
Suppose you want to calculate the minor of this element. This is A22, right? Second row, second column, right?
Yes, yes, yes.
So what you will do is you will eliminate the second row and the second column and calculate the determinant of the remaining submatrix.
Okay.
This one, A, C, G, I. You calculate the determinant of this. Do you know how to calculate the determinant of this?
It is AI minus GC.
Yeah. That's so this is what you do for minor of any element. So you eliminate the row and column in which it appears.
There is a formula minus 1 to the power I plus j. Minor of
that's
AI.
The cofactor.
Okay, minor of Aij means AI minus GC.
A minor of this element. Yeah, you have taken this element in particular here.
That means minus 1 to the power I plus j into AI minus GC.
Yeah. Now tell me what is the minor of this element here? How will you calculate it?
0, 0 to 4.
0. Why do you say it's 0?
0. Because 0 into 4 minus 0.
Yeah. Minor is 0.
Because the determinant is 0.
No. Whoever asked the doubt on minor, can you please answer? How did you tell that the minor of this element is 0?
Minus 1 to the power I plus j means what?
No, that's cofactor. That's cofactor. I'm asking about minor.
Minor of Aij is 0 into 4 minus 0 into 2.
Yeah, why did you take 0 into 4 minus 0 into 2?
Because I eliminate this row and this column.
Yeah. So you know how to calculate the minor, right?
Okay, now I understood.
Okay, fine. So you calculate the minor and then you multiply it with minus 1 power I plus j. Then you get the cofactor. And using the cofactor, you can find the determinant of the matrix. Okay. Then using determinants, what did we do?
Ma'am, would it be possible with the help of an example to show how to expand, column wise, because that's where I get confused.
You do the same thing. So what you do, suppose you want to expanding along the second column is easiest here, right? Because there are 2 zeros.
Yes.
Yeah. So when you take the first element, 4, into cofactor of 4. So what is the cofactor of 4?
Minus
2, 3.
Minus 1 power 1 plus 2 into determinant of eliminate the second row, first row and second column. 2, 2, 3, 4. And then plus 0 times 0 is here. This is minus 1 power 2 plus 2 into determinant of 1, 1, 3, 4 plus 0 times the other entry, this 0.
Ma'am, why are you taking separately for column? Is it anywhere mentioned or like?
No, they asked me for a column, that's why.
Okay.
You can expand along any row, but for this matrix in particular, expanding along the second column is the easiest, right?
Yes, that's why I'm asking, because there are instances where column wise makes more sense.
Okay.
Ma'am, why always plus? We know that there is a plus minus plus.
Yeah, there is a plus minus plus. You can, if you're confident about the plus minus plus, then it's fine. Otherwise, to be safe, you multiply with minus 1 power I plus j.
Okay.
Yeah, see, you can start with this entry is minus, right? This one. So you get minus plus minus.
This is the general rule. This is the general use that minus 1 to the power I plus j. Otherwise, I can directly apply through row plus minus plus, minus plus minus, and plus minus.
Plus minus plus, minus plus minus, plus minus plus. So this is the sign pattern. This is the sign pattern because when I do minus 1 power I plus j, this is what I'm going to get, right?
Yes, ma'am.
Basically, minus 1 to the power 3, that means minus.
Yeah. So this is how you expand along a column.
Yeah, thank you, ma'am. I got it. Thank you.
Hello, ma'am.
Yes.
Sorry, I was late. Can you tell me, did I miss something important?
No, we are just recalling week 1 contents.
Okay.
Excuse me.
What will be the weightage?
Weightage is equal for all weeks. It will be the quiz paper will be similar to the mock paper.
Okay, ma'am. It means 25% each.
No, we are not giving any percentages. It's equal. All topics carry equal weightage.
Ma'am, how many questions in total, ma'am?
Up to fourth week, ma'am.
Questions again. Everything will be similar to the mock paper. So you can start. Means you can watch the starting part of the session. I have told all this there. It will be very similar to the mock paper.
Ma'am, could you please explain the concept of system of linear equations?
Yeah.
I have one doubt in activity 1.3, question number 6. Please, can you explain it through the help of this example?
Yeah. So the determinants concept is.
I'm sorry, ma'am. Please explain first all the concepts. After that, question answer.
Yeah. We'll do concepts, questions related to the concept, and that way we'll do so that you don't lose track. What is A transpose?
Rows are converted to columns.
Row and columns are interchanged.
You interchange the rows and columns, and then we know that the determinant of A transpose is equal to determinant of A. And then what is determinant of C times A?
C times determinant
E power n.
Determinant of A.
Where A is an n cross n matrix. So for every row, the C is going to come out, right?
Ma'am, and if the number of columns are not equal to number of rows, then we just take the number of rows, right? C raised to n.
No, you cannot even find the determinant. No, you can find determinant only for square matrices.
Oh, right, ma'am. Sorry. Right, sorry.
Okay, then now maybe we'll go to system of linear equations and then get back to
just 1 minute. Can you just scroll up? Just a minute. Can you please scroll up?
Then for determinant, only these two are thumb rules, right?
A little more, ma'am. Just a little more. Yes,
yeah. So for determinants,
yes, ma'am. I know how to calculate the cofactors and minus, but what is this A11, C11 plus A? Can you just elaborate?
This is the determinant.
Okay.
Ma'am, we don't have the solutions to the mock test.
It will be uploaded.
Okay.
And for determinant, these are the only
tables, right? One thing more, we also don't have solution for graded assignment 4, ma'am.
Ma'am, there are more properties of determinants, right?
Yeah, there are more properties. We'll get back to it when needed.
Okay.
Yes.
Ma'am, that
so graded assignment solutions will also be up on the page.
Please map us whatever the important properties, ma'am, so that we can write it down.
Okay, you tell me because this is what contextually whatever comes to my mind, I just write that.
Okay, ma'am. Just explain which is more important for the quiz now.
Yes.
Oh no, whatever I'm telling is not related to the quiz in any way. I'm just trying to recall all the concepts. So if I miss out on any concept, you should tell me that I have missed out on certain topic. So I'm just doing a quick recap of whatever we have studied. This doesn't mean that if I miss out on some topic, it is not coming in the quiz, because I might have missed it out just because it was not there in my mind. Okay.
So there's one property. Determinant of inverse A P is equal to determinant of A. So,
when we talk about inverse, we'll come to that. Okay. Before that, when the determinant of A is non-zero, you say that A is an invertible matrix, right?
Yes.
Or non-singular. and when determinant of A is equal to 0, you say that A is a singular matrix. Okay. And when you have an invertible matrix, you can find the inverse of a matrix, right? A inverse exists if determinant of A is not equal to 0. And how do we find the inverse?
It can be by adjoint method.
Yeah.
By determinant of A into adjoint of A.
Adjoint of A.
Yeah. And what is adjoint of A?
This is a cofactor transpose of cofactor.
Ma'am, one question. And A not determinant of A not is equal to 0 means A is invertible. That means how it is connected with the solution actually, unique solution or no solution or
we'll get to that.
That will be linear of sister equation when we come to that.
Yeah, we'll discuss that when we come to systems of.
Okay.
Ma'am, the word singular just means non-invertible, or is there some other meaning to the word singular?
And also, ma'am, which terminology you are going to use?
Either of these, like we will mostly try to use invertible for invertible matrices and singular for singular matrices. But sometimes you can also see non-singular.
Ma'am, can you scroll a little up so that we can take a screenshot?
I will share the PDF immediately after the session.
All right. Thanks.
Excuse me, ma'am.
Yes.
Ma'am, what's the literal meaning of singular and non-singular except apart from determinant equal to 0 or not 0?
This has some connection to system of linear equations, but maybe let's not get to that. When the determinant is 0, you just say that the matrix is singular.
Okay, ma'am.
Okay, so calculating inverse is fine, right? You just calculate the adjoint matrix, that is the transpose of the cofactor matrix, and you divide by the determinant. So this is how you calculate the inverse of a matrix. Okay, so let's quickly get into system of linear equations. Okay, so when you have a system of linear equations, what is it? Ax is equal to b, right? You put the coefficients. Yeah, coefficients you put together, and that matrix is called the coefficient matrix. X is the vector of all the variables involved in the system, and b is the right hand vector. So what will be the order of the matrix A?
A square matrix.
It can
no, not necessarily square. It can be rectangular as well.
Yeah.
M is the number of equations
and N
is the number of variables.
Yeah. So the number of equations is the number of rows, and the number of variables is the number of columns of the matrix A. And then you're trying to solve the system Ax is equal to b. So how do you solve it? And what are the possible number of solutions you can have?
We can do by
solutions.
long
0, 1, and infinite.
Yeah. So you can have infinitely many solutions. You can have no solution at all, or you can have a unique solution. So unique solution means there is only one solution to the system. And when you're trying to find a solution, you're trying to find the vector x. So if suppose the vector x has components x, y, z, 3 variables, then you're trying to find one vector. You cannot say x is equal to 1, y is equal to 1, z is equal to 1. You cannot say these are 3 solutions, right? All these 3 put together is one solution to the system, right?
Yes.
So you're trying to find the vector x. So that is how you count the number of solutions. So it's a unique solution if you have only one solution. If it has infinitely many solutions, then in this case, if it does not have a solution, then it is no solution. Okay. So geometrically, all these concepts were explained.
Ma'am, can you please scroll up? I have a doubt in one property. Yes, it does.
Which one?
A inverse is equal to 1 by determinant A into ADJ A. But in the tutorial, there is a process. Actually, I watch in the tutorial that if I
using Gaussian elimination, right?
No, actually the matrix and along with the identity matrix. If I
Yeah,
want
yeah,
to
that's using Gaussian elimination. Yeah, we'll do
this way,
that.
using this process also I can calculate A inverse, no?
Yes.
Yes, yes, yes.
So ADJ A means ADJ
This is nothing but the transpose of the cofactor matrix. You know how to calculate the cofactor. Then you write down the cofactor matrix, which is nothing but the matrix, all of whose entries are cofactors of the corresponding entries of the matrix. So if you have this
ADJ by
matrix,
determinant A, that means I divide all the cofactors by determinant of A.
yes, yes. So this is a matrix, this is a number, you do scalar multiplication on this matrix.
Okay, I have to multiply 1 by determinant A with all the entries.
Yes, yes.
Ma'am, can you please take activity 1.3, question number 6?
Can you explain
It was on system of linear equations, right?
Yes, ma'am. Yes, ma'am.
Yeah. So yeah, we'll quickly do this.
Here, like there is some concept, right? If the number of equations is less than the number of variables, then it is infinite, like something like that.
Then the number of
It was
it's not
regarding linear
necessary.
dependence and independence.
So, ma'am, how can we find out that if it is unique, or you will come to that later, or it's not a part of this?
Yeah, we'll discuss everything.
Okay.
We'll come to that. Yeah. Okay.
Excuse me, ma'am.
So, yes.
So can you tell me the example of these three solutions? How can we find it? Unique, infinite solution?
Yeah, we will. So, did you watch the previous live sessions? Means the links that were shared along with the announcement.
Yes, ma'am.
So everything, a lot of examples are discussed there, right? Yeah, so that's why we sent out the announcement, because we'll not be able to cover all 4 weeks, a lot of examples for all topics in all the weeks. That's why we had sent out the announcement so that you can watch all the problems. Anyway, we'll proceed. You can go back and watch that anyways. Yeah.
Excuse me, ma'am. Can you explain how many solutions are in AX is equal to 0 homogeneous system?
Yeah, I will.
Okay, thank you.
Ma'am, I would suggest that if you can, please just keep in mind the important topics for the quiz and discuss in this session. And later on, you can take on the doubts if possible.
Yeah, okay. Actually, all topics are important. So, yeah, I think we should speed up, because weeks 1 and 2 were pretty easy and you've already done a lot of it.
Ma'am, that's what. Will it be 2 sessions or this will be the final session? Because week 1
this will be the only session.
Oh.
Yeah.
Because 3 and 4 requires more attention. So.
Yeah. So we are still in week 1, right? Or have we entered week 2?
No, we are still in week 1.
Okay. So by 8:45 or so, we'll finish these 2. Okay.
Yeah.
Okay. So when the right hand vector B is 0, it's called a homogeneous system. And in this case, you have only 2 possibilities. It's either unique solution or infinitely many solutions, right? Why is it so?
Because
the constants are 0.
X is equal to 0 is always a solution, right? So you always have a solution. It's only a question of whether that is the only solution or are there infinitely many solutions. So when the system is homogeneous, you have only 2 possibilities. You don't have the concept of no solution here. Okay. So now, if the coefficient matrix is a square matrix, how do you solve the system of linear equations? What is the method that you use?
Sorry, ma'am.
Yeah.
Ma'am, B is equal to 0 means all the constant term of the linear equations are 0.
The right hand vector is 0.
X plus y plus z is equal to 0. 2x plus y plus z is equal.
So you have a square system.
This part I couldn't get. Ax equals b. So b we are making it 0. So you mean to say that the x is always a solution?
Yeah, when x is equal to 0, this is always a solution, right? You want to find x, right?
Yeah.
X is equal to 0. You put x is equal to 0, that's always a solution to this system, right? If you multiply a matrix with a 0 vector, you're always going to get 0, right?
Yes. Yes.
And if A equals 0?
No, the matrix being 0 means all coefficients are 0. So in all the system means, what do you mean? Like, you mean this 0
A
x
is a
plus 0
A is
y
a
is 0.
matrix.
X is a vector.
This
Yes.
doesn't make sense, right? All equations are 0.
X is a
So
vector here.
basically, the right hand vector is a 0.
Oh, do you mean to say that Ax is equal to 0? So either A is 0 or x is 0?
Yes, yes.
No. No, A is a matrix, x is a vector. These are not numbers. You cannot tell that, right? You have a matrix and a vector, and then you multiply those two. You get another vector as an answer. The 0 is not a number. This is a vector.
Means it is a matrix, huh?
Yeah.
Vector.
You have an n cross n matrix, and then you have an n cross 1 vector or m cross n matrix. And then you have an m cross 1 vector, which is all zeros.
Oh.
Basically,
Okay,
ma'am is saying that x, y, and z all are 0. When ma'am is saying x is equal to 0.
Okay, x, y, z all are 0 and the coefficient can be anything. Okay.
Yes, coefficient is a matrix.
Yeah, coefficient is
The matrix.
Okay.
Okay, so if we have a square system with the determinant of the coefficient matrix being non-zero, we can apply Cramer's rule to solve, right?
Yes, ma'am.
And the solution is determinant of AXI by determinant of A. So what is this AXI?
X
Where
means
the
Coefficients
first column of A matrix is in the ith position.
Yeah, you replace the ith column by the vector B. So you do that and then you get a solution. Since the determinant is non-zero, you can use Cramer's rule and you know the explicit solution. So here you have a unique solution, right?
Yes. Here we have only one solution.
That is only one solution and you already know what the solution is. Xi is given by determinant of AXI by determinant of.
Solution means what?
There's only one solution to the system.
If determinant A not is equal to 0, then unique solution.
No, then we use Cramer's rule and then it's unique.
Ma'am, can you repeat what is AXI?
AXI is nothing but the matrix obtained by replacing the ith column by the vector B. You can just go back and check your notes. Everything is available there.
Hello, ma'am.
Yeah.
Fine.
Here you can go to the solve with us session of week 1.
Ma'am, everybody is speaking. We cannot get anything. So please mute all.
Is it possible to explain?
Yes, ma'am.
If possible.
Hello, ma'am.
If it's possible, what should I explain?
With one example, please.
So a lot of this has been, I feel vector space is a confusing topic.
Yeah, ma'am.
Yes, ma'am. Yes,
Vector space is really confusing.
Yes, ma'am.
The reference, ma'am, what you're discussing is already discussed. Means if somebody needs a reference, we have discussed this on May 13th, week 2 live session.
Okay.
So even the notes can
I've even sent the links, right? Along with the announcement, all the links have been
Okay, no issues, no issues. Please carry on.
I'll share the link in the chat section.
Okay.
Okay. And then another way, yes.
Can I ask one question?
Yeah, sure.
When you use Cramer's rule, that will be always give unique solution.
No, see, when you have a square system and the determinant of the coefficient matrix is non-zero, only then you can use the Cramer's rule. And when you use the Cramer's rule, obviously there is a unique solution.
Okay, ma'am.
It can also be the case of x is equal to 0.
Yeah. If it's a homogeneous system. Okay. So Gaussian elimination. What is Gaussian elimination? How do you solve using Gaussian elimination?
We have to convert the matrix in reduced row echelon form.
Yeah, you either do row echelon form or RREF, reduced row echelon form. And what is row echelon form? What is reduced row echelon form? All that is clear, right?
Yes.
So you convert it into REF or RREF, and then you solve the system. And
Actually, whole of the augmented matrix.
Oh, okay, fine. So you first write down the augmented matrix AB, and then you convert it into REF or RREF, and then you try to find the solution. You will get the solution from that. Okay.
Ma'am, why is it important to have an augmented matrix? Can it not be just A?
No, if you just do the operations on A, see what you're doing. Suppose you have a system like this. If you just do the operations on A, 1, 1, 1, 1, you're not going to convert it into another system which is equivalent to this system. Only when you do operations on the augmented matrix, you cannot just when you're doing elimination method, what do you do? Suppose you have this, you'll multiply, okay, say this also is 2, and say this is, okay, this is 1. So what do you do when you try to eliminate? You will multiply this entire equation by 2 and then add, right? So you don't leave out the constant. You multiply the constant also by 2. Yeah.
Right. Yes.
Okay.
This homogeneous equation, then we don't want.
If it's homogeneous, because this is going to be completely 0 all the time, it doesn't matter. Okay. So if you have a square system and if the determinant is not equal to 0, then it's going to give me a unique solution always, right?
Yes.
Yeah, and if the determinant is equal to 0, it may or may not have, means it may have a solution, it may have infinitely many solutions, but that we cannot tell. But one thing we can tell is if the determinant is non-zero, then the system is going to have a unique solution. So you know what the elementary row operations are, right? What are the 3 elementary row operations?
First one is row interchange. Second one is scalar multiplication. And third one is
yeah, you interchange a row with another row. You replace one row with the row times a row plus some alpha times some other row, and then another thing is you multiply a row by a constant. So these are the 3 elementary row operations, and you're allowed to do only these to convert any matrix into a row echelon form or a reduced row echelon, right? Okay. And then
ma'am, if the determinant of A is 0, then we have a unique solution, right?
No, non-zero. When the determinant is non-zero.
Okay.
Ma'am, while interchanging the rows, is there a change in the signs, ma'am?
Yeah. So what are the effect of elementary row operations on the determinant? When we do this operation, the determinant changes sign, right? This is with respect to determinant. Means you're allowed to do only elementary row operations to get the row echelon form or reduced row echelon form. But the effect of elementary row operations on the determinant is what I'm telling you now. So when you interchange 2 rows, the determinant changes sign, right? And what is the effect of the second operation on the determinant?
I think it's no change.
No effect.
Yeah. So there is no change here. And what about this one?
Multiply by C.
Multiplied by C.
Yeah. So C times the determinant of the matrix that we started with. So
but then there would be no sign change in the third case also, right?
No. In the third case, it's going to get multiplied by C. That's it. If the C is a negative number, then it's going to change sign. But
ma'am, in first
operation,
ma'am, in first operation, whether it is we are changing to any row, whether we are changing from 1 to 2 or 1 to 3, the sign changes from first.
Yeah.
Okay.
Yeah.
Does it matter on the number of times we change the rows, ma'am?
Yeah, every time you change, the determinant changes sign. So if you do 2 interchanges, then the determinant is going to remain the same sign, right? When you do twice.
Suppose, ma'am, we are changing first row and third row. Then the sign will be changed twice or
no, once, right? You're just doing one interchange. R1 is replaced with R3. That's it. One interchange. So the sign is getting changed by once.
Okay.
Ma'am, if I'm doing from 1 to 2, it will be minus, and from
Yes,
2
of course.
to 3
That is
it
what
is
she is
again.
repeating again and again. Please don't ask. She has
Yeah, so
repeated 3 or 4 times.
R1 with R2 you interchange, there will be a sign change, and then you interchange R2 with R3, there will be a sign change. But directly R1 to R3, there will be a sign change once. That's it.
Ma'am, if delta A equals to 0, are there only 2 possible solutions then?
If delta is equal to 0, you will either have no solution or infinitely many solutions.
Okay, thank you.
Okay. So I guess we are done with weeks 1 and 2, right?
Ma'am, what is the difference between row echelon form and reduced row echelon form?
Reduced row echelon form. Okay, row echelon form is you want the pivot, the leading non-zero entry in each row to be 1. And then the number of zeros in each row should be greater than or equal to the number of zeros in the previous row. And then all the zeros, zero rows should be at the end and all that. In reduced row echelon form, whenever you have a pivot, all the elements in the column containing the pivot should be, all other elements should be 0. So see, if you have a row echelon form, this is what you want. So you can have something like this. But in reduced row echelon form, since this is a pivot, you want this entry also to be 0. That's the only difference. You can go back and check. It has been discussed in detail.
Ma'am, and just one clarification with regards to pivot. So whenever we have a pivot, so that particular x or y variable will be dependent or independent, something like that?
Okay.
Yeah.
It depends upon
So
the...
when you do the Gaussian elimination, so you find the RREF of the matrix, and whenever there is a pivot in a column, so the variable corresponding to a column containing the pivot, is independent or dependent?
It depends. If
I think
column
it's
only the pivot element is present and the elements above and below it are 0, then the variable is dependent.
Yeah, that's because it's an RREF. Anyway, that's the case, right? When you have a pivot, the column containing the pivot will have only one non-zero entry, and that will be the pivot, right?
Yes, you can say yes. It derives to this only.
So the columns containing pivot, the variables corresponding to those columns are dependent, and whichever column does not have a pivot, those variables are all independent, right?
In all cases, we can't calculate.
Just a short question, which would be discussed later. I think you would be discussing later in this topic. I want to ask whether Sir has mentioned in one of the live sessions that the number of independent variables is equal to the rank of the vector space.
Ma'am, let ma'am come to the vector space.
Let's get to that later.
Yes, ma'am. Please come to week 3. We have a lot of problems.
Yeah, okay. So there was someone else asking some question here.
Thanks, ma'am.
Ma'am, can a matrix and multiple row echelon
so
forms?
that
one second. Let's finish her question.
Ma'am, why is it so that the variable corresponding to the pivot is dependent? Like, what is the reason or logic?
So when you have a pivot, so you have something like this, right? So this is the pivot, and then you have this. So this equation will be something like this: y plus, okay, suppose this is x.
What is
so you'll have y plus 2z is equal to something, some variable, say some number. So you can write y as 2 minus 2z. So that's the reason. Yeah.
Okay, ma'am.
In this equation, y is dependent and z is independent.
Yeah, because the third column did not have a pivot. Yeah.
Ma'am, in all cases, we can't find RREF, no? In some cases, we have to stop at row echelon form. Is that correct?
No. Every matrix can be converted into REF or RREF. Both you can do for any matrix.
Got it. Thank you, ma'am.
Ma'am, can you discuss with one rectangular matrix? Is it possible?
Row echelon forms?
What is it? Can you please repeat?
Can a matrix have multiple row echelon forms?
Row echelon form, yes.
And reduced row echelon forms is unique, right?
Yeah. Okay.
Is it possible?
So here the first variable. Yes.
Is it possible to discuss one rectangular matrix for REF or RREF?
You want me to solve a problem?
No. Diagonal. We are making square matrix diagonal one. When it comes to rectangular matrix, how it will? That's little tricky.
No, it's
He
still
can
going to be
refer
this
to
case,
the
right?
previous sessions.
So you will have something like this. So in this case, this is an RREF, rectangular matrix.
Okay. It need not be the same, no? Third column also can be one, right?
Third column?
I think we
No,
need to see
you
row
want
wise.
RREF, right? You want RREF. So yeah, if there is a pivot, all other entries should be 0.
Okay.
Yeah.
Ma'am, one quick question.
And using
Ma'am, for example, like we have a okay, we have a like
please mute if you're
system of
not
linear
talking to me.
equation.
Yeah, please go ahead with the question.
Yeah, if we have like a system of linear equation, and as we have multiple methods to solve those question, right? So is there any like particular sequence in which we can tackle that question? Like we have Gaussian elimination method, Cramer's rule, and then we can solve those questions by the inverse matrix as well.
Yeah. So I'd say Gaussian elimination covers all cases, so you can go ahead with Gaussian elimination.
So
you needn't check whether the determinant is 0, non-zero, or anything for Gaussian elimination.
Okay, so only that
I personally feel I'll personally prefer Gaussian elimination.
Ma'am, even when Shubham sir was taking the session, he also stressed on Gaussian elimination. So would there be any compulsion, like we have to choose any of the three?
It's your choice.
Okay, fine.
See, you can even do this, what we used to do in school. It doesn't matter. You can choose your own way of solving a system of linear equations.
Okay.
Yeah, thank you. And using Gaussian elimination. Yeah.
Okay, ma'am. Thank you.
Okay. So using Gaussian elimination. Yeah.
Please let her complete. Yes, ma'am.
Okay, so using Gaussian elimination, how we calculate the inverse is you just adjoin the matrix with the identity matrix. And then you convert the A matrix.
Ma'am, please mute all. Yes, ma'am, can please mute all for once.
Revision, they also.
उन्हें तो पूरी जगह डालने जाता समर्पण
So to find the inverse, what you do is you do the elementary row operations to convert the matrix A into the identity matrix. So what you get on the right side is the inverse of the matrix. So yeah, this is week 1 and 2. Let's if you have any questions, just for 7 minutes, not more than
what
that.
you just explained. What you just explained.
So to find the inverse of a matrix using Gaussian elimination, you can do this. So you write down the matrix, you adjoin the identity matrix to the right. So if you have a 3x3 matrix, you add the 3x3 identity matrix here, and then do Gaussian elimination. Use elementary row operations to convert this matrix into the identity matrix. So while doing that, you will make some changes on this matrix too, right? When you do the row operations. So those changes will get converted to the inverse of the matrix that we started.
Ma'am, it is
okay, got it. Now got it, ma'am.
Ma'am, first line you wrote A/Y. It is similar to augmented matrix, right, ma'am?
In augmented matrix, you add a vector. Here, yeah, you are adding a matrix.
Matrix of the same order.
Augmented matrix is a term that we specifically use for system of linear equations.
Okay, ma'am.
Yeah. Here it will be a matrix of the
same order.
She is referring to AX is equal to B. A into X is equal to B.
Yeah.
Ma'am, in this matrix, the last column wherein you have written 1, 1, 2. So if it would have been 0, 1, 1, then can I say that there is no leading coefficient in this column? If it is 0, 1, 1.
No, even if it was 0, 1, 2, whatever was earlier, even then there is no pivot there. No, you've exhausted all the rows. You've already found 3 pivots. That's it, right?
And
please
what
look
if
row wise.
4 by 4 matrix? Then
4 by 4, it is
0, 0, 1, 1.
possible that you will get one more pivot.
Hmm.
So are you
And if
telling
the
3 by 4? 4 by 3, say.
no, yes, ma'am. 4 by
Even
4.
in this case, it's possible on 4 by 4, you will have one more pivot. You can have one more pivot.
So if apart
It's
from the
4
leading
plus 4.
coefficient, the other elements are 1, then can I say that we have a
No.
leading
If it is
coefficient?
RREF, you will make it 0, right? If you
Okay.
want to convert it to RREF, you will make it 0.
Okay, ma'am.
Ma'am, one more doubt.
Yes.
You suggested to use Gaussian elimination method, right? Suppose if we need to answer whether the system will have unique solution or infinite many solution or no solution, then how are we going to tackle that?
So once you get the Gaussian elimination, means use the Gaussian elimination, you already get the solutions, right?
Yeah.
So using that, you will know whether it is a unique solution or.
Okay, through
Using
the
rank
dependent
also.
and independent variables, right?
No. How do you solve using Gaussian elimination? After you do the reduction, know how to find the solution, right?
Yeah.
So once you get the solutions, you will know whether there are infinitely many solutions or how many solutions and all that, right?
Ma'am, can we discuss Gaussian elimination for 1 minute, please?
Ma'am.
Yeah. So is
We
there
can
any
discuss everything, but
question
time is so limited. So it will be better if you can go back and watch the Solve with Us assignment and Solve with Us session. That will be
Ma'am,
very
after
helpful.
getting the solutions through Gaussian, how to gauge whether it is a no solution or a unique one? Like
it is already discussed in the Big 2 Solve with Us session. Please go back and see.
So there is only 3 minutes left for week 1 and week 2. So let's discuss only one question.
Hello, ma'am.
What is the difference between RREF, RREF and Gaussian elimination?
Yes.
Hello, ma'am.
I request you to take an example of a rectangular matrix. Take a rectangular matrix in Gauss elimination.
Okay, fine. Let's stop here then. So, this is already in reduced form, right? This is in row echelon form,
Okay.
right?
Let us assume that it is in this form. Then please discuss the solution.
So how will you find the solutions? Y plus z is equal to 2.
Yeah.
So y is equal to 2 minus z. See, when there is an independent variable, it means there are infinitely many solutions, right?
Yeah, right.
There is no pivot in this column.
Okay.
Which means that there is an independent variable and hence there will be infinitely many solutions.
Okay.
Then you will substitute this back in the first equation. X plus y plus z is equal to 3. Y plus z is 2. So x is equal to. So the set of solutions is 1 comma
I
2
think this
minus
is not
z
yet in
comma z.
reduced row
Or you can
echelon
put
form.
z is equal to k.
Ma'am, this doesn't look like it's in reduced row echelon form.
It's in reduced echelon form, not a reduced row echelon.
Yeah, it's in row echelon.
This is in row echelon form. This is not in row.
So we can do it even with REF.
Okay. When I talk about independent variables, I want it in RREF. Okay, fine.
Ma'am, is there any condition clearly that how can I decide from a matrix that which one is unique solution, which one is many solution, and which one is zero solution?
Yeah, you once you study about rank, there is a condition, right? But that's not there in the quiz syllabus. Right? There is a condition which you will study later. Yeah.
Okay, ma'am.
So I guess we'll go ahead with the spaces.
Like this. Otherwise, I have to solve at the end.
What is it? Yeah, you solve it like this and then
just you solve like this, x plus y plus z equal to 3.
Yeah.
Unless until I solve properly, I cannot say that there is a many
No,
solutions.
that is what difference between row echelon form and reduced row echelon form. If it is only row echelon form, then you have to use this type of equations. If you do reduced row echelon form, then directly you will get answer.
Okay, fine. So yeah, when you do row echelon form, you have to do back substitution. You have to go back in every equation and then substitute and get the answer. Reduced row echelon form, you will do a lot of computations on the matrix itself that you will get the solution directly. Okay, fine. So that's week 1 and 2, and there are a lot of discussions already done on that. So let's get into vector spaces. What is a vector space? When do you say something is a vector space?
When
You
it
need a set
satisfies the 8
and 2
axioms.
operations.
It need to.
Yeah, you want. You first want a vector, a set. Along with that, you want 2 operations that are defined on the set. One is the plus addition, and the other is the scalar multiplication that we have. Yeah. So you in our course, vector spaces are all real vector spaces. That is over R. That is when you do scalar multiplication, you are multiplying with real numbers, right? Throughout our course, for us, it's all over real numbers. Yeah. So it is a vector space if it satisfies not 8, 11 axioms, right? 11 or 10, right?
8 axioms.
So the first condition is that it should be
8 axioms and 2 conditions.
Yeah, 8 axioms and 2 conditions, addition and subs.
That is when you add 2 elements. Yeah. What is it?
Okay, continue.
So it should be closed under addition and it should be closed scalar multiplication. These are the first things you will check. Is there a lag during me late or something?
Yes, ma'am. There is a lag in your voice.
Yes, ma'am.
Oh. Okay, fine. Let's see if it gets corrected. Okay. So vector spaces. First of all, if you take any 2 elements from the vector space from the set V and add them, it should again belong to the set V. And when you do scalar multiplication, that is, you multiply an element of the vector space with a number, it should again be in the same set V. So these are the first 2 conditions that you should check. And then you have the 8 axioms. So the first axiom is, okay, I'm not writing down the axiom. You have 8 axioms. I'll just mention those. Well, the first one is commutativity of addition. V1 plus V2 should be equal to V2 plus V1. This should hold for all elements. And then associativity. V1 plus V2 plus V3 should be equal to V1 plus V2 plus V3. It shouldn't matter in what way you add the vectors. And then there should be a 0 element. It is a 0 element if it satisfies. So in all these cases, the plus that we write or the scalar multiplication that we put should all be the one that is defined in the problem. Whatever is the plus that is defined in the problem.
In the end, it should be V.
0 plus V, V plus
Oh,
V equals to V.
Yeah, it should be. And then there should be an additive inverse. That is, there should be an element with which if you add this vector, you will get the 0 vector. So these are the 4 axioms relating to addition.
May I pause you for a moment?
Yeah, sure.
These last 2 conditions, the presence of 0 vector and presence of additive inverse. Ma'am, can we say that when additive inverse is present, then 0 vector is also present? And vice versa, if 0 vector is present, then additive inverse is always present.
You cannot talk about the last condition without the 0 vector. What is this 0? So you cannot tell if the additive inverse is present, then 0 is present. Means first of all, there should be a 0. Only then you can talk about additive inverse.
Okay, ma'am.
You are adding that element and you're getting a 0. What is this 0? That is because of the third condition.
That is the resultant.
And then with respect to scalar. So and then the conditions with respect to scalar multiplication. When you multiply a vector with 1, you should get back the vector. And then you multiply, then there is a combination. A plus B times B should be equal to AB plus BB. So this is distributivity, distributive property over addition and scalar multiplication. Similarly, we have for this other property, AB1 plus AB2. And then the last property that says you can multiply in any order. So if all these conditions are satisfied, then the set V along with the two operations that is defined, plus and dot, is said to be a vector space.
Oh, ma'am, is there a
so now let's
could you give a counter example for the fourth property and the third property, like if where it
there
was
were
possible?
examples, right, where the zero element is not present and all that.
Oh yes, ma'am, but actually it is like quite
And
mixed.
I think geometrically it is possible. Subhasis sir have shown us that.
Okay.
What is
that affine flat example in which we don't have zero present, I think. Right?
Yeah.
Yeah.
Okay, fine. So yeah, this one, right? That 1, 5 if we take. I think in this example you won't have the zero.
Yes, ma'am.
Means with respect to usual addition and scalar multiplication.
Yeah.
So usual addition means vector means component wise addition, and usual scalar multiplication means component wise scalar multiplication. So now what I want is I want a vector v1, v2, which I add with 1, y. I should get what 1, y. So when am I going to get that? For one thing, v1 has to be 0, right?
Yes.
Or okay, v1 and v2 have to be 0. Only then I'm going to get this.
Yes,
yeah. But 0, 0 does not belong to this set, right?
Yes.
Yes.
Because if it belongs to this set, the first component has to be 1. Yeah. Okay, so maybe quick questions on vector spaces. Any doubts here? Vector spaces, examples of vector spaces.
I have a
A
doubt.
lot has already been discussed. So.
Excuse me, ma'am. This example is.
Can you see
not
what
in
is R here? R is it is real number or anything else?
Real numbers.
Is obviously.
Yeah, there was someone else with a doubt, right?
Yes, ma'am. I have a doubt in dimension.
Ma'am, in this
dimension.
We'll get to dimension.
It is not discussed yet, no?
And the last axiom.
We can move in a systematic way. Right? Yeah, please.
Ma'am,
Okay, no problem.
Doubt. Is this example given by you, is this a vector space or no?
No, this is not a vector space.
It's not okay. Yeah, that's what I was thinking.
Because the zero element does not belong. There is no zero element in the vector space.
Yes, thank you.
Ma'am, if someone can put in the chat where the vector space has been discussed, the links of the session, that will be great.
So you can quickly open discourse and search for the post by Shubhajit, the one that he posted today morning. All the links are available there.
Oh.
Someone can maybe copy from. Yeah, it's all there. Yeah.
What is that?
There are four links for week 3 and 4.
In the mail also it has come. Same thing, right?
Yeah, same thing.
Okay, then it's fine.
Okay. So once we know vector spaces, what is a subspace?
Excuse me, ma'am.
Yeah.
Ma'am, as you earlier discussed, in this particular example, vector W, V1 and V2 are not belonging to W because they are equal to 0.
No, I was trying to get an element which acts like the zero element. If it acts like the zero element, this plus this should give the same vector, right?
Yes, ma'am.
That is possible only if this V1, V2 is 0, 0.
Okay. So, ma'am, zero vector is not found in any vector space or only in this particular example?
No, 0 is present in R2, right?
Yes, ma'am.
If it is not present anywhere, then we won't have vector spaces at all, right?
Yeah, ma'am. So in this only in this particular example, zero vectors are not present.
Yeah, this is with respect to the usual addition and scalar multiplication. If you change the addition and scalar multiplication the way it is defined, then you can make this a vector space actually. That is also there in one of the activity questions, where this is actually a vector space with respect to some other addition and scalar multiplication.
Okay, ma'am. Thank you.
So, ma'am, why zero vector is always
Ma'am, can you give some more example of vector space?
Okay. We'll make the same set a vector space. Yeah, someone was asking some other question. No? 0, 0. What is that? Is it related to
Yeah,
this
ma'am.
question?
Why zero vector is always unique, ma'am?
No, you cannot have two zero vectors, right? Like you can prove that the zero vector is unique, but yeah, logically, let's keep it logically now that you cannot have two zero vectors, right? You cannot add like then which is zero plays an important role, right? So which one will you choose if you have to?
You mean to say that we cannot have two origins, right? This is what it means.
Yeah.
Geometrically,
See, origin means for R2 it is this origin, but if you look at some other abstract space, this need not be the zero vector at all. Yeah, I'll give you that example. So now take the same set.
The example we just discussed.
If we will take in higher dimension, then it will be different. It could be different.
So now suppose you define addition like this. So 1 comma y1 plus 1 comma y2 is defined as 1 comma y1 plus y2. Is the definition clear?
Yes, ma'am.
Yes.
And scalar multiplication, c times 1 comma y is 1 comma cy. So now the definition is completely different. Here it is not a vector space. Now using these operations, this is a vector space.
Yes, ma'am.
Check that this is a vector space. What is the zero element here?
1 comma 0.
1 comma
1 comma 0.
1 comma 0 is the zero element.
So this is unique here.
Okay, ma'am. Now we got it.
So based on the operations, the same set is not a vector space and is a vector space at two different instances. So it's based on the operations.
Hello, ma'am.
And we can we also say the way the definition is given will also define whether it is a normal addition or a vector addition.
No, see, here also it is vector addition only, but it's just that we are doing component wise addition there. Here we are fixing the first component. We are not disturbing it.
No, what is the difference?
The way addition is defined is itself different.
Hello, ma'am.
Yeah.
No. Actually,
Why 1 comma 0 is zero element in this question?
So why don't you try it? So what do you want? 1 comma y plus b1 comma b2 should be equal to 1 comma y. This is what you're looking for, right?
Yes.
Yes.
How do you add this?
1 plus v1.
1 plus b1.
No, it's not 1 plus v1. First of all, for this element to be in this set, v1 has to be 1, right?
Yes. It will be always 1.
Yeah, so it's going to be 1 plus means 1 comma v2. So for it to be in the set, it will become 1, and then you add this. So this is going to be 1 comma y plus v2.
So, ma'am, in the question,
v2 will be 0.
In the question, that will be given addition or multiplication.
Yes. It will be mentioned. In case it is not mentioned, you choose usual addition and scalar multiplication. It will always be mentioned, but in case it is not mentioned, it is always the usual addition and scalar multiplication.
One quick question means like we have changed 0 in this case. Likewise, can we change 1 of multiplication? Means scalar multiplication 1 also get changed while solving such type of questions. Because
no. See, the scalar multiplication 1, that is the real number 1. That's not the vector. This is a real number. So this is the usual 1 that we have. That cannot change.
So it will be always 1. Means like in
this
addition,
is
0
always
changes.
1.
Okay.
This is a vector. This is a number.
Okay.
And this is the number 1.
Ma'am, actually, I didn't get the difference between the first one and the second one. Example, first one you are telling that it is not in vector space. And second one, you are telling.
The way it
Yeah,
is
because
defined.
the operations are different. No, here it's usual addition. Here the addition is completely different. So you just sit down and work out all the axioms for this. Everything will be satisfied. But here we have already seen that the zero vector does not belong to the space.
Here we are defining it as usual addition. Okay.
Yeah. Okay. So let's get to what is a subspace. What is a subspace? It's a subset of a vector space, which in itself is a vector space, right?
Yes.
Yes, ma'am.
Satisfy all the axioms of vector space.
So all the axioms of a vector space should be satisfied for W, and this will be a subspace, subset of some bigger vector space. So what is nice about subspaces is that we needn't check all the axioms, right? You need to check whether the zero element belongs to W. You need to check if W1
it is closed on addition.
Yeah.
And it is closed on scalar multiplication.
Yeah. So you just check these, then it's going to be a subspace. It's a subspace if and only if these conditions are satisfied. You needn't check all the other axioms. So you just check these three and then it is going to be a subspace. Okay, fine. And after subspaces, what do we have? Linear independence, is it?
Yes.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay. So what is a linear combination?
Ma'am, sorry to disturb. Can we discuss subspace with an example?
This is a subspace, right? This one.
Any vector space with any subspace.
Just take the bigger
At
space.
particular dimension, yeah.
But you should talk about the same operations there in R2, in the sense that you shouldn't change the operations for the bigger space. Or let's take this, no? Take a simpler example. Take V to be R2 and W to be the x-axis. This is a subspace, right?
Yes.
But ma'am, W can be natural numbers.
No. How can it be natural numbers?
Natural number. Sorry. Natural number is not a
You can
vector
multiply.
space.
Yeah. You can multiply half with half, right?
Yeah.
This does not
I
belong.
got it. That was a mistake.
Okay. And what do we know about the intersection of two subspaces?
And it will be a subspace.
Yeah. The intersection will always be a subspace, but the union need not be a subspace, right?
It will only will be a subspace if it is a subset of one another. Right?
Yeah.
It will be different.
It will be a
on
subspace only if it is, if one is contained in the other. Okay, fine. So what is linear combination? Suppose you have a set V1, V2, Vn, some set. When do you say a vector is a linear combination of these vectors? So suppose you can write V as alpha 1 V1 plus alpha 2 V2 plus etc. alpha n Vn. We know this belongs to V, right? Because of the closure property of addition and scalar multiplication. If V is a vector space.
Yes.
Yeah. So if you can write V as a combination of these vectors where all these are constants, means numbers, real numbers, then you say that V is a linear combination of V1, V2, etc. V. So in short, if we want to write, V is alpha I, Vi, I is equal to 1 to n. So if you can write V, if you can write V, yeah. What is it?
I thought your voice was breaking. Maybe it was only for me, or was it for everybody?
It was only for you, brother.
Yeah.
Only for you.
Sorry.
Oh, no problem. Yeah. So you have a set, and if you can write a vector in terms of elements of this set by using constants and this addition and scalar multiplication, then you say that the vector V is a linear combination of these vectors V1, V2, Vn. So when do you say the set is linearly independent or dependent?
When the solution is only zeros.
Okay, fine. So the actual definition, by definition, if we go, the set is
Linear
linearly
combination is
dependent.
0.
One is
The
a
set is
scalar
linearly
multiple of
dependent.
the other.
If one of the
Not
vectors,
always.
The scalar multiple of the other hand is 0.
Let ma'am complete.
Let ma'am complete.
yeah, I'll tell it. Yeah. So if one of the vectors can be written as a linear combination of the other vectors in the same set, then you say that the set is linearly dependent. Or in other words, if you can write 0 as a linear combination of these vectors with at least one coefficient being non-zero. Is it clear?
Yes, ma'am.
What linear dependence is? Yes. So now when I have vectors, I'm going to have some components, right? Like B1, if it is a vector in R2, it's going to have two components, right?
Excuse me, ma'am. I have a doubt.
Yeah.
Yes. So you said that with at least one coefficient not equals to 0. Now, what if I take Vi to be a 0 vector? Then I can take all the coefficient. I can take all the coefficient as zeros except the ith one, which is the
Coefficient
0th.
of Vi.
Yeah. So in that way, though, we can express any vectors as a linear
That is
combination.
a linearly dependent set, right? Because any vector containing the zero vector is linearly dependent, just because of the reason that you told me.
Yeah, this is understood.
Oh, okay. Thank you.
Yeah, any set containing the zero vector is linearly dependent.
Ma'am, I've got one doubt.
Yeah.
You said at least one should be non-zero. So this is where my doubt is: how can just one element being non-zero can give 0 actually?
At least one element is non. At least.
At least one coefficient should be non-zero, isn't it? And
Yeah.
rest are
So
0.
it's actually two coefficients, but how do you define whether a single set is linearly independent or not? For that, keeping that in mind, the definition says at least one.
Okay. Now I got it.
Yeah.
Ma'am, what does it mean? Any set contains 0 is linearly dependent. 0 means 0 vector.
Yeah. So if you have V1, V2, Vk, and then 0, this is always going to be a linearly dependent set because it contains the 0 vector. So why this is linearly dependent and all that has been discussed in the specific session. Yeah. Okay. Yeah. So if you have,
Ma'am, for a second, can you scroll up for linear combination part? Just for a second.
I'll share the PDF after the session.
Okay, ma'am. Okay. Thank you.
Yeah.
Ma'am, where it will be shared?
In the supplementary contents. You will find it in the supplementary contents tab.
Okay,
If you have zero vector, it is linearly dependent, correct?
Yeah. That's because you can put the coefficient of 0 to be some non-zero number and all other coefficients to be 0.
But ma'am, why
Like
always we equate linear combination to 0 for checking linear dependent and independent? Oh, that's
Let's take it as definition. The reason and all has been explained in the session. So why it is 0 and all that.
And you told about the coefficient non-zero for a 0 vector. What if the coefficient is also 0?
No. See, what do you want to? You want to find at least one non-zero alpha, right? Such that you can write it as 0. Means such that this entire combination has to be 0. You just want to find one. See, 0 times V plus 0 times 0 is also 0. But using this, you cannot tell that this set is linearly independent, right? Because this is also possible.
Yeah.
So you just need to find one combination where you have at least one non-zero coefficient.
Okay.
Yeah. And when do you say it is linearly independent?
When we have all coefficients
Every
as 0.
coefficient
Yeah.
is 0.
So if 0 can be written as a linear combination of these vectors, then all the coefficients have to be 0. It's just the opposite of linearly dependent. Then you say the set is linearly independent. Now, how is this connected to system of linear equations?
It is connected to homogeneous system of linear equations because we are expressing
So
0 vectors combination of other.
Yeah. So this all these elements vi.
Please, I'm not able to get what they are saying.
Yeah, I am going to repeat it. Yes. So all the vectors that we started with, the set that we started with, they are all subset of a vector space. So suppose let's take the vector space to be Rn or R2, R3 or anything. Okay. So when it is in this case, when the vector space is Rn, each of these vi's is going to have n components, right? This is how each of the vectors are going to look. And now when I write down this, I'm going to get a system of linear equations, homogeneous system of linear equations, right? Agreed?
Yes, ma'am.
Each of the vectors has n components. And this is equal to the 0 vector. Because of this, I have a system Ax is equal to 0, where what is x?
It is the number of variables. Number of variables.
It is the coefficients. Yeah, it's the coefficients in this linear combination. So I have a homogeneous system. I always know that this has a solution. The question is whether it has a unique solution or infinitely many solutions. If it has a unique solution, the set is
Linearly independent.
Yeah, it's independent because if it has a unique solution, the solution vector has to be 0, which guarantees this. And if it has infinitely many solutions, the set is linearly dependent. So this is linear dependence and independence in terms of this vector space Rn. So now if the coefficient matrix is a square matrix, to check whether a set is linearly independent or not, all that I need to check is the determinant, right?
Yes,
Determinant is equal to 0.
The determinant is 0, I will have infinitely many solutions.
Ma'am, sorry, ma'am, just after Ax is equal to 0, can you please repeat, because just missed it.
So now, is it clear that you can write this linear combination as a system of linear equations Ax is equal to 0?
Yes.
Yeah. So now if the system, this is a homogeneous system. So it either has a unique solution or it has infinitely many solutions, right?
But ma'am, why only homogeneous, madam?
No, because I'm putting equal to 0, right? That is what my linear combination is equated.
B is 0.
Okay.
Yeah. No. Once 0 comes means you have unique or you don't have, you are infinitely many.
Yeah.
Because
so if it has a unique solution, then the set is linearly independent. If it has infinite, one second. If it has infinitely many solutions,
Ma'am
it
has
is
written already.
Yeah. Yes. What is it of?
Ma'am, if determinant is equal to then no solution, what is the condition for no solution?
No, there is no question of no solution at all, no? When you have a homogeneous system,
right?
Yeah.
So
It
there is
either has a unique
invertible and non-invertible. If determinant not is equal to 0, then invertible. And equal to 0 means non-invertible.
No, that is different. Now we are dealing with independence and dependence of vectors in terms of determinant. Yeah, what you're saying is right. When the determinant is not 0, the matrix is said to be invertible.
That means solution, has solution.
When the determinant is non-zero, there is always there is a unique solution.
Can you write, because many people have this confusion, can you write with respect to matrix? It will be easy for them.
No, but what should I write with respect to matrix?
Write one matrix and then x, y, z, and if you equate that to the constant ABC, if all the ABC becomes 0, then you only have unique solution or infinitely many. That's it. That's it.
But there it is variables,
Ma'am,
here
we
it
have
is
done it a
coefficients.
lot of times.
Yeah, the homogeneous part.
No, you can write
many times. Please go back and watch the live session.
Or yeah, that's clear.
Please do that. Yeah, you will be get clear.
Okay, so now we will take questions up to this linear independence and dependence, and then we'll continue.
Ma'am, so can we say that if it's a square matrix, we should first find out its determinant, and thereby we'll be able to do it. And if it is not a square matrix, then what is the option? Only Gaussian elimination?
This is a good question. Even for rectangular matrix, how to proceed?
You do Gaussian elimination. You do Gaussian elimination and check whether it has unique solution or infinitely many solutions. If it has a unique solution, then it is independent. If it has infinitely many solutions, then it is dependent.
Ma'am, generally, if we get an identity matrix by the time we do the Gaussian elimination, when we reduce it to, when you convert to RREF, then usually that would be a unique solution, right?
No, we will get
some.
Yeah.
If you're getting identity matrix, it means the system is a square system. Why do you do Gaussian elimination? Just find the determinant, no, in that case?
Sorry?
If you're doing Gaussian elimination and getting identity matrix,
yes,
it means it's a square system, right?
Yeah, okay.
Okay. Why do you do all this? Just find determinant.
After getting the solution from Gaussian, how do we find that it's unique or this? I'm just getting confused in that.
No, if you have
find the solutions. You know how to find the solutions.
Yes, ma'am,
right?
I know that. But later on, how to know if it is unique or infinite?
It is written, no, if it will be independent, if it is unique, it will be dependent if it is infinite.
No,
No. The question is when you do Gaussian elimination, how do you find whether it has unique no solution and all that, right?
Yeah, after I get the solution.
Okay. So suppose you have a 0 row, completely 0 row. In this case, there are infinitely many solutions, right?
Yes.
Yes. Because the last equation is not giving you. And then suppose you have a 0 row in the A part, but a non-zero entry here. This is not possible, right? 0x plus 0y plus 0z cannot be equal to 1. So in this case, there is no solution, right?
Okay. Yeah. Yes.
When you don't have a 0 row, or
won't come in homogeneous, right? So you can.
In homogeneous it won't. But our question was in general, right?
Yeah.
Ma'am, I have a doubt. Ma'am, may I ask it?
Yes.
Yeah. I have a doubt from a really early session part.
Okay.
Can we write a column vector in the form of a square matrix, square vector?
No.
I think you can.
A square vector?
No, because it was, I guess, in the first mock session where we had to find the values of a column vector. I mean, we had to find the inverse of a column vector. So how would that be possible?
No, you cannot find the inverse of a column vector, no, because column vector is not square, first of all.
Yeah, exactly. So that is why I was having this problem. So, and the
what was the question?
I'll just check real quick and I'll just let you know. Just wait for a few seconds.
Maybe we'll do some questions from the mock quiz till this topic. This one is simple, right? You just find out solutions.
Yes,
we'll ignore week 1, 2 and all that, because all that you can do.
Ma'am, it was a vector A equals to 2, 3, 1 was given. That's a column vector.
Okay.
And there was another vector C which was given, which is another a column vector, x1, x2, and x3. Now, basically we had this dA equals to C. Okay, this equation was given, BA equals to C. Now we were asked that what was the what did B represent? So
is this
basically,
from mock?
Yeah, mock for week 1 and 2. So maybe in
Okay.
the end you can just do this. It was from mock for week 1 and 2. It is question number 15.
15. Okay. 15. Okay, fine. Okay, A
Yeah,
is
this one.
given. Oh no, you're asked to find the matrix B such that we will get this. So A represents the vector corresponding to the tourist from Manali. So from Manali you have here 2, 3, 1. You have that vector, and then you're given C, which is the column vector representing the number of tourists to Manali in 2020. So after the reduction happens, there'll be some number of tourists to Manali, right?
Yeah.
Yeah, so what is the matrix which is actually going to help you find the number? That reduction matrix. That's going to be the matrix of all these entries, right?
And this type of question also will come now because this was solvable.
Yeah, comprehension type will come. Yeah.
Okay, so the answer would be this 0.5, 0.5, 0. Okay.
That you should check.
Just calculate the reduction from the basic, and you will get the matrix.
Okay,
yeah, so it's
basically
going to be this one, I guess. Yeah.
Because it is multiplying 1 cross 3 into 3 cross 1.
Yeah. I get it now. Basically,
sorry, 3 cross 1 into 1 cross 3. So a matrix is 3 cross 3 result. When you will multiply, you would get this.
What I was trying to do was basically from that equation B equals to C, I was trying to find B by taking A on the other side, which would require me to find the inverse of
no.
You cannot do that, no?
Yeah. That is why I was
data is already given in the question. You have to calculate the reduction.
Yeah.
Ma'am, the question like question number 1, which is shown in the screen, if there is a such type of equation and the solution is no solution, unique and infinite, then I have to solve it first reduced row echelon form, then I have to recite.
Try to calculate the determinant first. Half of the question is solved.
Here it's a square system. No, but if you calculate the determinant, you're going to get only the unique solution part. Actually, see, it's obvious, no? X plus Y plus Z is 3. Even if you do your school level calculation, you will get the answer.
Correct. So this type of solvable question also you do in the quiz.
Yeah, it will be like here you don't need time at all.
It's a long way that I just ask you that is there any shortcut method or any means? Can we decide that there is a no solution, unique solution?
If you write down the system in the matrix form, it is already in the reduced, not reduced, in row echelon form. So you know the solution straight away.
Yes. Reduced row echelon form I can solve.
Ma'am, I have a question. Like in this mock, we were supposed to give answers in this form 1, 2, 3. So most of them were actually MSQs rather than MCQs or NATs. Okay. So that becomes a little tough because you end up making a mistake and getting it all wrong, even if you write the whole sequence wrong.
Yeah, that's right. You have to be careful.
So would that be expected even in this quiz 1?
Yeah.
And why do you ask the questions this way? You can ask them the simpler way. The result doesn't matter. Only the result.
There's a part. See, if we give you an MSQ question, there is high chance that a lot of people get it right out of fluke, right, or at least partial marking. But in this way, you can get it right only if you know all the correct answers.
Ma'am, sometimes you know the answers, but then in just typing out the solution, you can make a mistake in this particular order.
Otherwise, you can do the.
I want to make a request. In IITs, while taking the offline exams, you give marks for the steps, but we don't get this chance that we get marks for some steps, at least some partial marks for correct answer, even if.
No, for in statistics,
chance is not given to us.
It's not discuss all this in this section.
Yeah, let's finish the revision. Yeah.
Okay, ma'am, can you please explain me again Gaussian elimination?
Gaussian elimination.
Yes,
you want me to explain Gaussian elimination?
Yes, ma'am.
Did you watch the previous session videos, the links that had been sent on the announcement?
Yes, ma'am, I work, but can you explain me in Hindi?
Yeah, can I do it at the end of the session so that we finish everything else?
Yes, ma'am.
Yeah.
Okay.
I have a doubt regarding linear independent. Can I ask?
Yeah.
So, ma'am, what I understood from your explanation, that if the combination of vector addition and scalar multiplication are zero, then it is linearly dependent if at least one coefficient of that particular equation is non-zero, right?
Yes, yes.
Yeah. So, ma'am, I think it's written somewhere that any set of 4 vector in R3 is linearly dependent.
Yes.
So how it is possible? I am not able to get it by this particular explanation. What I understood from linear independent, the definition.
Yeah. So if you have any set of 4 vectors in R3, so you have 4 equations, right?
Correct.
4 equations and 3 variables. So you have a 4 cross 3 matrix. You have a homogeneous system. So now, when you do the row echelon form, what are the maximum number of pivots possible?
3,
right? So which means that there is one independent variable, right?
Okay, so yeah.
So you
eliminated. Okay, got it. Thank you.
That means free variable, right?
Free is not
free variable. Yeah, independent variable. Yeah.
So it means that that equation is independent.
The variable is independent, which means there are infinitely many solutions. Okay, so the second question, I guess it's pretty simple, straightforward. You can do it. Then, yeah, let's ignore week 1 and 2. Then this is dimension we haven't discussed. Which of these are subspaces? So if it has to be a subspace, you're not allowed to have numbers like this, right? 1, square, all that is not allowed, right?
Yes, ma'am.
So that is the
Why so?
You are not allowed to.
Yeah, ma'am. Can you just explain?
Because
subspace should contain 0. Right?
Yeah, the subspace should contain the 0 vector. That's all. Because if this has the 0 vector, it should satisfy these two conditions. 0 plus 0 plus 0 is 0, but 0 minus 0 is not 1.
Okay, because
so
this is
the subspace.
It follows usual addition and scalar multiplication.
Yeah. Usual addition and scalar multiplication. Yeah.
Okay, that is why these numbers are not allowed.
Yeah.
Which
and
one?
Even squaring is not allowed, no?
Ma'am, what's wrong with that?
1 and 4.
Ma'am, but the last one, 0 plus 0 plus 0 square is 0, right?
Yes, ma'am. Yes,
yeah, that is fine. 0 vector belongs, but what other things will be a problem here?
Ma'am, imaginary numbers, because there is a square.
No, why imaginary? It won't be closed under addition, right?
Yes, ma'am. Yes, ma'am. It won't be closed under addition.
See, x1, y1, z1 belongs to w, and x2, y2, z2 belongs to w. Then x1 plus x2, y1 plus y2, z1 plus z2 should also belong to w. But when you do that z1 plus z2, I'm going to get z1 plus z2 squared, whole squared. I don't know whether the z1, z2 part is 0 or not, right?
0 and 1 will hold good.
Yeah. So say if I have x comma y such that x plus y squared is 0. I reduce right. So in this case, suppose x1, y1 belongs to w and x2, y2 belongs to w. So in that case, I know that x1 squared plus y1 squared is 0. x2 squared plus, not squared. x2 plus y2 squared is 0. Now I want to check whether x1 plus So now I want to check whether x1 plus x2 plus y1 plus y2 squared is equal to 0 or not. I cannot conclude this just with this information, because here I have y1 squared plus 2y1 y2 plus y2 squared. So because of this reason, you're not allowed to have square, cube or anything. You're allowed to have only power 1 for the variables, and you're not allowed to have constants also. The second one is a subspace clearly, because this is nothing but the x-axis. Oh no, it's in R3, so this is the xz plane. So the xz plane is a plane passing through the origin, and
how do you know it is in?
It is
Okay, it is given. It is in R3, right?
yeah, x, y, z. Yeah. Okay, and then span of this set. Yeah, let's discuss span and then come to this. Suppose A is a matrix with okay, fine. The statement 1 you can do. Statement 2, V with respect to these two operations, is it a vector space or not?
Ma'am, being a mod,
how do we do this?
Is not closed on addition, I suppose.
Yeah, when you do mod, no, it won't be. Okay, it's easier to check scalar multiplication. So scalar multiplication will be a problem.
Does not exist. First of all, check
Which
the inverse.
Additive inverse, is it?
Yes, additive inverse is not present because it would never be negative.
Okay, fine.
Right, ma'am. First of all, if we
no,
check
but what is the guarantee that see, this vector space is going to have only okay, fine.
Modulus, ma'am,
no, it's not necessary that it should be negative, no?
No, even if it is negative,
okay, fine.
Mod gives positive.
Okay, fine. When you have mod, the easiest thing to do is check scalar multiplication. Huh? What is it?
Ma'am, why for the statement 4, ma'am, isn't the dimension like 2? I didn't understand how it's not 2.
We'll get to that. We haven't discussed dimension yet, right? The set is linearly independent or dependent?
You were saying something about mod. When it is mod, when a mod is given, it is easier to check scalar multiplication.
Yeah, because when you multiply by a scalar, it's going to come out as a positive number, no? But in scalar multiplication, you're going to have a negative number.
Okay. That's very clear.
Independent, I guess.
Dependent. Very dependent.
This one, the statement 4, this set is dependent, right?
Dependent because second one is 0, 0.
Multiplication of the first.
So
the
the
dimension
other
will reduce, right?
for statement 2, if you take the example x1 y1 and minus x1 minus y1, okay, so if you do addition, the x1 it should be commutative, right? It is not commutative. X1 plus x2 is 0, minus x1 minus x1 is minus 2x1, so it's not the same, so it should not be a vector space. Statement 2 is not a vector space.
X1 y1
minus x1
x1 y1 and
minus x1 minus y1.
Okay, no, but
so
it's still commutative, right?
So no, if it is x1, x1 plus minus x1 will be x1 minus x1, 0, right?
Oh, okay, fine.
Okay, if you do it the other way, minus
okay,
x1 minus x1.
Okay, fine. Yeah, that's a good one. Okay. So addition is not commutative.
Yeah.
Okay. And then this one, is this a vector space?
Ma'am, I didn't understand that statement, how we check it. The mod one, I really don't get it.
So you just write down that addition is not commutative and then check it why.
Yeah.
Addition is not commutative. That is V1 plus V2 is not equal to V2 plus V1.
But aren't we taking mod? Since we're taking mod, won't the answer be the same?
Condition is given. They have to prove that it is not correct.
Sorry?
What is it?
Condition is given in the mod. It is not given in the mod that it has to be in the mod.
But if we do commutative, maybe x2 minus x1's mod, won't it be the same answer?
No. See, so what he was telling is x1 y1 plus minus x1 minus y1. You take this. This is going to be mod x1 minus x2. That's going to be plus x1, comma mod y1 plus y1, right?
Yes.
Right?
Yes.
What about the other way? Oh, even then we are getting the same. Yeah, addition is commutative in this
Yes,
case, right?
that's what I was thinking because of the mod
If
it's
sum is
commutative.
always positive, then 0 will not exist
You
for
can
every
check
vector.
associative.
Sorry.
You can
Ma'am,
check
if sum is
associative.
always positive, then 0 will not exist for every vector.
I think I was wrong.
0. Yeah. So
Ma'am, you can check
x1,
associative,
y1.
commutative, not associative.
No, see, whenever there is mod, there's some scalar multiplication involved that's going to play the trick. So take some vectors x1, 2, and then say minus 2 times this plus 2 comma 1. Say something like this is minus 2 times 1 comma 2 minus 1 is 1. So this is minus 2 comma minus 2. But what is minus 2 times 1 comma 2 plus minus 2 times 2 comma 1? This is always going to be a positive number, right? Because when you're adding, I'm going to get a positive number, right?
Yes.
Yeah. So that way, whenever there is a mod, it involves scalar multiplication. The problem is because of scalar multiplication. So this is going to be 2 comma. These two are not equal. That's all.
Yes, sir.
Yeah.
So we have proved it.
Huh. Any set of three vectors in R2 is always. You didn't understand what?
Last step alone. Can you please explain again?
I just did this.
I didn't understand
Minus
how
2
to
times
come
this. This is how the addition is defined. No, you take this minus this and then take the modulus, the difference in magnitude of these two numbers.
Okay.
Yeah.
Ma'am, in the first, I think it is 3 comma 3, right? Not 1 comma 1. When it comes to the addition. Oh.
1 minus 2 is minus 1. Mod of that is 1.
Oh, ma'am, it's plus, right? It's not minus. I mean, I'm not able to get.
This is not.
How is it defined? Minus, no? x1 minus x2.
Okay. Yes. Okay.
Statement 3, any set of 3 vectors in R2 is always linearly dependent.
You just
Yes,
explained
right?
while discussing Gaussian.
Yeah. Any set of n
Statement
vectors
4.
in n plus 1 vectors in Rn. We
Statement
haven't
4.
discussed dimension yet, so we'll come back
Okay.
to this.
Okay.
So
Thank you.
statement 3 is true. Means it's right.
Statement
Ma'am,
3
can
is
you,
true, yeah.
ma'am, can you just discuss the next question? I mean, the next one. I mean, I know we haven't done span. I mean, the Q statement. I mean, I know we haven't
Which
done
one?
span yet.
Q.
Statement Q. Why is this true? Can you just explain it to it? Can you just explain?
We'll do that. When I discuss span, I'll do this.
Okay, ma'am.
I'll explain this problem. Yeah. Okay, what about statement P? In vector spaces, we are not allowed to multiply also. That's another cheat code. Means you cannot multiply stuff like this. So you can check that this is not a vector space.
And if we multiply, then what axiom is violated?
Some distributive property will go off. Means addition over scalar multiplication or scalar multiplication over addition. Some of that I think will be disturbed.
Okay, so we are.
I don't think it will be closed with respect to. Yeah, it won't even be closed with respect to addition, no? Means what is the guarantee that x1 plus x2?
It is the guarantee. It will be closed under addition. Because
x1, okay.
Yeah. It will valid
okay,
because
okay.
of
I think
addition.
even we won't
Not
get
be a problem.
0 plus v is equal to v plus 0. I think even
Where
that we
is
won't
the
get.
ma'am? Where is the
Yeah,
0 plus
yeah.
v.
we are also not getting the additive
Yeah.
inverse.
0 plus v
We
will
won't
not.
get the 0. 0 plus v will not be equal to 0. Means will not be equal to v.
Madam, in terms of properties, it is fine, but we can define addition like that: x1 comma x2 plus x2 comma x y2 is equal to x1 x2. That is the definition, right?
Yeah, you can define, but the question is, with respect to this definition, is it a vector space or not?
Yeah, correct.
Are you should ask.
The properties may not actually follow, and that, maybe because of that, it may not be vector space, but the definition of addition is fine, right?
Mm-hmm.
Yeah, it could be anything.
You can define. It's the definition. You can do whatever you want to define.
Ma'am,
Ma'am,
can you just
if
write it
instead
out?
of
satisfied.
v equal to r square, if we mention v is a subset of r square here, will this be true?
No, v is equal to R2. V is the plane.
So what I'm saying is that instead of v equal to r2, if we mention v is a subset of r2, will this statement be true? Will this be part of the vector space?
Can you discuss
So
span
even
and
then, the 0 element has to be in the space, right? Even if it is a subspace, the 0 element has to be in the space, for which we are not getting a 0 element at all.
Ma'am, can't we have 1 by x1, 1 by y1 as a 0 element here?
No.
No, my bad. Can't we have 1 comma 1?
Okay, will it work? Yeah, 1 comma 1 will work.
Yes, ma'am. 1 comma 1 works as the additive inverse and
additive identity.
And 1 by x1 by 1 by y2 works as the multiplicative inverse.
Okay, fine.
We have
What
to
will
find
the additive inverse be then? x1 y1 plus x2 y2 is x1 x2 comma y1 y2. So what will the additive inverse be?
1 comma 1.
Sorry,
Identity is
inverse.
1 comma 1. Inverse will be 1 by x1. 1 by x1.
So it is not valid when x1 x2 is 0.
0, yeah.
So that's why I think it is not valid for v equal to r square.
R2, yeah.
Ma'am, can you tell another thing? 0 should be a unique, like for all the elements x comma y belonging to a certain
if you have a vector space, the 0 vector is unique.
Okay. Can you tell a condition where this is not obeying? Like, I mean, can't come across some axiom which is not following.
The additive inverse, no? The
Additive inverse exists, right?
What is
1
the
by
additive?
x1 and 1 by y1.
No, what if x1 is 0? What is the additive inverse of 0?
There is a condition of 0.
Sure, yeah.
it is 0 x1?
What is it?
Ma'am, additive inverse of 0 1 is 0 minus 1 because then only it will make it 0.
No, addition is defined like this, no? x1, x2.
Oh, okay, you are.
y1, y2. This is how addition is defined.
Okay.
Ma'am, can you just please write the whole sum out? It's really confusing when, I mean, if you're just telling it so.
Okay, so I want the additive inverse. This is going to be the additive identity. Additive identity. Then what is the inverse of this? So this plus some element should be equal to 1 comma 1, right? Then this is the additive inverse.
Yes.
But when I add these two, what do I get? 0 comma y1. This can never be equal to 1 comma 1.
Okay, ma'am, got it.
Yeah. Okay, then this is fine.
11, 12, 13.
Can we discuss 11?
11, 12, 13.
What is difficult in this? You just have to do the calculation, right? Oh, this is a system of linear equations. You'll get a system of linear equations, right? You just write down V1, V2, V3. You're going to get 3 equations, right? Then you have a system of linear equations. You have to solve it, right? 12 again a system of linear equations, right? You put it, you just write down what is the system you get from here. You will get a system of linear equations. Write it in the matrix form. Find the cofactor. Find the solution.
This was little lengthy, ma'am.
Was it? Okay, anyway, the solution will be uploaded. You can check with the solution.
Yes.
I don't, I had
Oh,
prepared
it
the
is not
solution,
lengthy
it looks
actually.
small. Anyway, the solution that I had prepared has a different data. So you just have to change the data. The numbers are a little different because it was dealing with money and we had negative numbers earlier. So we just changed the data a little. Anyway, the process is the same. Okay. And then what about this one? Suppose V is a vector space spanned by the column vectors of A. Okay, you get A and then column vectors of A. And then you have to check whether it is linearly independent. How do you check whether it is linearly independent or not?
Check the determinant.
Yeah, you have 3 vectors in R3. Yeah, just check the determinant. Yeah, and every subset of a linearly independent set is linearly independent, right?
Ma'am, one question
Yes,
here.
ma'am.
Where is it mentioned that it is in R3? It is nowhere mentioned.
You can see it is in R.
No, 3. It has 3 components. No,
Yeah.
1, 2, 3.
R3 means what? There is 3 dimensions. 3 components.
No, 3. This could be dependent.
How?
No, ma'am. In question, we have to check whether it is linearly independent or dependent, right?
Yeah. You can check the determinant and then check whether it is independent or dependent. I don't know. It could be dependent as well. After
Yes,
checking the
that's what I am saying.
It is
But
not.
it is no. We cannot say from looking at this that it is in R3.
Yeah, we can say it is in R3.
R2.
No, it is in R3 because each vector has 3 components.
Okay, ma'am. So see the second option. Look at the second option. First option and second option are exactly same. Either it could be dependent, it could be independent. So
Yes.
Suppose numeric is changed in this and it becomes a dependent. Okay. We cannot say that it is in R3. Then it is in R2.
No. What is R3? R3 is the set of all vectors of this form with 3 components. Because it has 3 components, it is an R3. Oh, you mean 3 vectors? No, 3 components.
Yeah, he is confused between
1, 2, 3. Not because of 3 vectors. See, this is a subset of R3. Yeah, this is also a subset of R3.
Okay, yes.
Ma'am,
From here we can say that it is in R3, right?
Yeah.
Ma'am, please
explain what?
That is why.
Third option.
Okay. So suppose it is linearly independent. Suppose the set is linearly independent. Then every subset is going to be linearly independent, right?
Yeah.
Yes.
Yes, ma'am.
Yeah. So if it is linearly independent, option 3 is wrong. And if it is linearly independent, option 4 is also wrong because I know every subset is linearly independent, right?
Please repeat.
What I am telling is every subset of a linearly independent set is linearly independent. And the other way for dependence, every superset of a linearly dependent set is linearly dependent. This is clear, right?
Yes.
Okay,
This is known.
It's obvious.
This has already been discussed. Yeah. So using this concept, you can check those 2 conditions. Means
please discuss the span and rank, ma'am.
Yeah. So yeah.
So, ma'am,
Too much of dependence and independence.
we have to make matrix in column wise, na? From these vectors. We have to arrange arrange these vectors in column wise. When when there is a equation, we can put it as a row wise, the coefficient, and whenever these vectors are given, we have to arrange it column wise to find out row issue.
You can actually put it row wise also, because determinant of A is equal to determinant of A transpose, no?
Okay. So there is no issue, means if we solve
Because of that you can.
Okay, row wise or column wise, it will not make any sense. That change.
Between the third and the fourth option, we can say that the third option will always be wrong, because if it turns out that they are linearly independent, the third option is wrong anyhow. If it is linearly dependent, then we cannot comment whether the subset would be linearly dependent or linearly independent, right? So the third option in every case would be wrong.
Yeah, because I know that every proper subset of this is not linearly dependent, because if I take a singleton element set, singleton 1, 2, 3, that is a linearly independent set, right?
Yes, yes, yes.
So
And
the
the
third
fourth
option is wrong in any case.
And the fourth one may or may not be right, depending whether these three are linearly independent or not, right?
Yes.
Okay.
Yeah. Okay, fine. So now let's discuss span of a vector space. What is span? Span of a set. How do you check?
Independence.
You just take the set. Huh?
Linear combination.
Set of vectors whose linear combination
Set of
gives the vector.
all
vector
finite.
which gives all the linear combination of vector space.
Possible linear combinations.
Yeah, you just take the set of all finite linear combinations of the set of vectors that you started with. That is going to give the span, and this is span of a set is always a subspace, right?
Yes, ma'am.
It's a vector space. So the span of a set is always a subspace. And then what you do in span is you just take the set of all linear combinations, finite linear combinations of the set. Okay. And what is a basis? Now that we know what is a span. Okay, what is a spanning set? What is a spanning set?
A set which spans a certain set. So that's
entire vector space.
So if you start with a vector space, S is said to be a spanning set if it is a subset of V, such that span of S is V. Then you say that S is a spanning set for the vector space V. Okay, so now we know linearly independent set and spanning set. What is a basis?
Can spanning set contain both linear and independent vectors?
Yeah. Any, you just need to span. That's it. It has to cover the entire space. It can have linearly independent vectors, dependent vectors. It doesn't matter.
So, ma'am, span I understood, but the spanning set, please give one example.
So if you take R2, can you give a spanning set for R2?
Yes, ma'am.
1, 0, 0, 1.
Yeah, x-axis, y-axis. Oh, okay. I just want one set. Yeah. So 1, 0, 0, 1. This is a spanning set for R2, right? Because any element in R2 can be written as a linear combination of these two vectors. Okay. This is also a spanning set, right?
Yes, ma'am.
Yes, ma'am.
This is also a spanning set. I can write AB as A times 1, 0 plus B times 0, 1 plus 0 times 1, 1. This is also a spanning set, but this is not linearly independent, right?
Ma'am, how it is a spanning set?
So that is,
so it will not form a basis.
Yeah. Someone was asking about spanning set. What was it?
1, 0 and 0, 1 is a spanning set. Ma'am, 1, 1 if added, then how it will be spanning set?
I have written any element of R2 as a linear combination of these three vectors.
Okay.
Right?
Yes.
Yeah. Okay. So there is an unnecessary vector here which could have been omitted. That is where the concept of basis comes into picture. So this is the maximal linearly independent set linearly independent set
Minimal spanning.
or a minimal spanning set. So the minimal spanning set, in the sense that the minimum number of vectors needed to span, that is a basis, and the maximum linearly independent vectors you can have, that is a basis. So this is basis, and any two bases have the same number of elements, that is the dimension of a vector space, which sir has also called rank of a vector space, but ignore the term rank. Let's keep call it dimension. Dimension of a vector space is number of elements in a basis, in any basis.
Ma'am, cardinality?
Yeah, the number of elements. The cardinality of a basis is the dimension. Number of elements. Cardinality.
Number of
What do you mean by
Dimension
minimal,
and cardinality are same. Na?
ma'am? What do you mean by
No,
minimal?
cardinality means number of elements.
Ma'am, please explain minimal spanning set.
Just 1 second. Cardinality means number of elements. So cardinality of a basis, the number of elements in a basis, is the dimension of a vector space. Yes, someone was asking about basis minimal spanning set. What was that?
In respect of set, cardinality means number of element, and here
yes.
Okay.
Yeah.
Ma'am, here could you please repeat this maximal linear independent, how it forms basis?
I'm not explaining why a maximal linearly independent set is a basis.
No, I
Take
mean
this
that.
one.
What do you mean by minimal spanning set?
Yeah, I'll tell that. So maximal linearly independent set means you have a set which is linearly independent. You add one more vector to it, it becomes linearly dependent. So any vector you add to the set, it's going to change independence to dependence. In that case, the set is said to be maximal linearly independent. You're not allowed to add any more vector. Once you add, it loses its independence. And minimal spanning set means the minimum number of vectors needed to span. You remove one vector, it's not going to remain a spanning set anymore. Is it clear?
Ma'am, it means that both are same only, no? Like what do you say that maximal linear
Yeah,
independence?
these two are equivalent, and they are equivalent to being a basis for a vector space.
Can I ask one question here?
Yeah.
Ma'am, in dimension, what is the role of sometimes an equation is given or two equations are given? Suppose y equal to 5x and all that. So how is it related to dimension? Suppose we are not given the spanning set, we are given the equation. Suppose, can you write one question?
You have to find a basis.
Okay, I can. Please, can you write one set? Suppose v2 is equal to a set xy such that y equal to 5x.
Okay. And then?
Ma'am, it is a set xy such that y equal to 5x. You have not written the set.
This is in R2.
Write the set xy.
Okay, fine. It's a subset of R2.
In one of the live sessions, sir has said that in this equation y equal to 5x, y is dependent upon x, and x is the independent variable.
Yeah.
So the number of independent variables is same as is equal to the dimension of the vector space.
Yes.
Can you explain this? Can you explain this concept? Because in graded assignment question number 5, the same concept is applied. Can you explain this concept? I am not clear about it, and because we are not given the spanning set.
Okay. Do you agree that y is dependent on x?
Yes, ma'am.
Is x dependent on y? X can be written as 1 by 5 times y, right?
Yes, ma'am.
Yes.
So x and y, you need to find the set of all x and y such that some condition is satisfied. If you know x, do you know y?
Yes, ma'am.
Yeah. So this is okay. If I know x, y is 5x, right? So this is nothing but the set of all. I can take x outside 1, 5, such that x varies, right?
Right.
This will be 1.
Right.
Till this point, it is clear.
So this is a basis, right?
Okay. It is the basis of only.
Because
it can be
this
only
is
the basis.
the spanning set.
Okay, we have created a spanning set from this equation.
Yeah, I've created a spanning set, and then I check whether it is linearly independent. Obviously, it is linearly independent because I have only one element.
Okay, ma'am. Ma'am, can I discuss?
Here, take this example. Here, can you give me a spanning set? After I write down this, I have a spanning set, right?
Yes, ma'am. This is a spanning set.
But this is not linearly independent because I know that 3 vectors in R2 cannot be linearly independent.
Yes, ma'am.
So this is not a basis.
Yes, ma'am. This is not the basis.
Now I will try to reduce one of the vectors. Let me say I remove this.
Yes, ma'am. I
Is it
know
still a
because
spanning
adding
set?
one. Yes, ma'am. It is still a spanning set. Now it becomes the basis.
Yeah, because I cannot remove one more vector and still span R2.
Yes, ma'am.
Ma'am, in your example, this basis can also be written as 1 by 5, comma 1, right? That would also be a basis, right?
Yeah.
Basis can be infinite.
Yeah.
Ma'am, does this vector have a 0,
3,
base
15,
here?
anything like that.
Ma'am, can you discuss question number 5?
Yeah, 0, 0 is there, no?
Ma'am, so like while deciding that whether
Yeah,
0,
I'll discuss
0
question
is there,
Ma'am,
like,
question number 5 of the graded
yeah, I will
before.
discuss.
Please later.
Yeah, I'll discuss that.
ma'am, so whenever we say that 0, 0 is present, so that time that xy should belong to R, right? Only then we say that it's 0, 0 is there, right? Otherwise, we don't say that.
I did not understand.
Ma'am,
0,
like ma'am, presence of a 0 vector. So, like, how do we gauge that here if it is there or no? Like,
Because it is
so
subspace of
this
R2.
is
So it's
R2 with respect. This is the subspace of R2 with respect to usual addition and scalar multiplication. And we know that in R2, this is the 0 vector. This vector should be in this space.
okay.
This is nothing but a line passing through the origin, right?
Okay, ma'am. Yeah. Okay.
Okay. Let's discuss question 5 of graded. Deadline is over, right? Yeah.
Yes.
Ma'am, please
which is the question? The numbers may be different.
Question number 5, ma'am.
No. The order may be different in mine.
Ma'am, it is the same.
This one.
Yes, ma'am. This one.
Okay. 9x1. So tell me what you will do here. Here you have a relation in terms of x1 and x5. So you can write one in terms of the other, right?
Yes, ma'am.
So one of the variables is dependent on some other variable.
Yes, ma'am. Suppose
now from this.
So two variables are independent and
ma'am,
no,
nothing
3
has
are
been
independent, no?
Nothing has been said about x3.
Yeah, so it's independent, no? There is no condition on x3. It can be anything.
So okay, ma'am, when a x3 is not given or it is not related in this equation, then we can assume that it is the independent.
It is independent, no?
Okay.
Can you just tell me what the equations are? Something such that 9x1 plus 9x2, what 9x5 is 0, and then
anything you can take. It doesn't make any difference.
4x2.
Yeah.
x1 is equal to minus x5.
Yeah. So from this, I'm trying to get a spanning set. I'm just trying to get a spanning set. I can write x1 in terms of x5. Okay, x1, x2, x3, nothing is mentioned. x4 is minus 4 by 9, x2. And then x5 is
minus x1.
Minus.
Yeah. So x1, x2, x3. This is x1 times 1, 0, 0, 0, minus 1.
Plus not getting
x2 times.
How have you written the first step, ma'am?
We have taken common x1.
Yes, ma'am. Yes, ma'am.
I'm using these two conditions.
You have written x1 as x1 and x2 as
x2 as
x2. Independent,
x2.
you have written x3.
x3 as x.
x4 you have written in terms of x2.
x4
and
from
x5
here.
in terms of x1.
Okay. Yeah. and then I'm just splitting it 0,
Same as
comma
she
1,
explained
comma
the
0,
previous
comma.
question. Let's take an example. Same way she explained.
What is it?
To the previous question, ma'am, you have taken. You have explained same way. It's just that these have 5 elements. Yeah.
This is a very nice way of explaining. I was not able to relate what is the relation between these conditions, spanning set, and dimension.
Yeah.
Now
So
I
now
have
you've
got
got a
something.
spanning set.
Yes.
And then you have to check whether it is linearly independent. If yes, then it is a basis.
By
Okay, then now the dimension is 3, right?
Yeah.
Can you check the answer, ma'am? Once it is
can you complete this
It
question?
is
4.
That's it. It's over, no? You've got 3 vectors. You have to check whether it is
Okay.
linearly independent.
By Gaussian elimination method.
Yeah.
Any value of x1, x2, x3.
It will actually be linearly independent.
Okay. But the actual method is Gaussian elimination method. We have to check it.
Yeah.
Okay, thank you.
I think you'll get straightforward.
Yeah, that's
0,
sure. Yeah,
1,
you can.
0. Yeah, I think it's already in that form. Yeah. Pivots.
Ma'am,
this
do
is
we
3.
have to find all these because there are 3 independent variables, and based on that we can directly say the answer is 3, right, ma'am? Do we have to?
Yeah. It's this reason, for this reason, because there are 3 independent variables. I'm going to get, see, I cannot eliminate any one of these variables. I need all the 3. So this is a minimal spanning set. So we have got a basis.
Ma'am, can you solve this without, if there are no conditions are given?
Number 4 of graded assignment 4.
And this is
One
reduced by
second,
echelon
can you
form.
give a?
Ma'am, can you solve this if the let us assume there is no conditions are given, like 9x1 plus 9x5, that 4x1, those conditions not given. You are simply having x1, x2, x3, x4, x5. So then if that is the case, what will be the answer of the dimension?
Dimension is 5, no? Because
5.
each of the components
Okay.
can be anything. There is no
So
relation.
we just have to split it by x1 into 1 0 0 0, x2 0 1 1, like that. So 5.
Yeah.
Okay. So every question
That
has
will
to
be
be
R5,
solved.
right? And the dimension of
Yeah.
R5 is 5. Yeah.
Okay. Thank you.
Question also
Based
in
on-
grade. Last
based on the
question.
Question 4 of graded assignment.
Ma'am,
No, what is the 4th question? Is it this?
Can
Yes,
you
ma'am.
move to the page that you are solving? You was writing.
Okay.
Ma'am, there from the second equation, we 4x2 plus 9x4 equals to 0. We had found x4 equals to minus 4 by x2. Sorry, minus 4 by 9x2. We can't write. We can't write like this. That like x2 equals to minus 9 by 4.
Yeah, you can do.
Okay.
You can do that also. In that case, you would have had it in terms of x4. That's all.
Yeah.
You will get a different basis there. Here you will get a different basis. Okay, find the rank of the matrix.
Yes, ma'am. This question.
So we'll discuss rank and then get back to this.
Yes, ma'am.
So we'll maybe quickly take questions on dimension, span.
Ma'am, that question which was in mock for week 1 and 2, that statement, that statement QV, that question.
Span.
Yeah.
This one, right? Here in this mock, right? This
Oh
one.
yeah. This one. Sorry.
So you have a condition AU plus BB plus CW is equal to 0, and there is also a condition that AC is not 0. AC is not 0. So is it clear that UVW is a linearly dependent set?
Yeah.
Now you want to prove span of UV is equal to span of UW or VW, I guess. Yeah, AC is not 0. Yeah. So what should you prove? If you want to show 2 sets are equal, you want to show one is a subset of the other, right? Means.
Yeah.
I'll show one, you show the other. You show this one, okay?
Okay.
Okay. So let me take any element in span of UV. So let some D belongs to span of UV. How is it going to look? Some alpha times U plus some beta times B, right?
Yeah.
Okay, fine. Now I want to show it is in span of V comma W. Can I somehow eliminate U and bring in W?
Yeah, we can just write V equals to minus CW minus AU by B.
No, I don't know whether B is 0 or not, but I know AC is non-zero. So A is also not 0, C is also not 0. So I am allowed to divide by A or C, but I am not allowed to divide by B because I don't know whether B is non-zero.
Okay,
I can
so
write U as
U as
minus
a
CW
function.
minus. This is in span of V comma W, right?
Yeah.
Ma'am, can you please repeat the second line, please?
Which one? This one?
जो AU plus BB plus CW is equal to 0, where AC is not equal to 0. After that, you got span of UV.
No, this is to prove.
Okay.
This you have to prove.
Yes.
So to prove that two sets are equal, I will show that first set is a subset of the other. This is a subset of this one. This is what I want to prove, right?
Yes.
So I am showing the first one. You can show the second one. The first one is I am taking an element in span of U comma V. I am showing it. I want to show it is in span of V comma W. So that's what I'm doing here.
Yeah, and for that purpose, what you did, like here alpha times U and beta times P, you did, right?
I'm just taking an element in span of UV. It's going to look like this: alpha U plus beta V, right?
Yes.
I'm just doing some manipulation to get it in terms of V and W. Using the relation that is given. This is given to me. Similarly, you have to show the other way around.
Ma'am?
Is it clear?
Hello, ma'am.
Yeah.
Ma'am, can you please explain once again what is maximum linear independent? I cannot understand properly.
Maximal linearly independent set. So you have a set which is linearly independent. Now the question is whether it is maximal linearly independent. To check that, what you do is
if a vector element with only one element non-zero and others are zero, then I call it maximum linear independent.
No. What is it? If a vector.
Okay. Yes, I thought that.
No, what was your question?
What is maximum linear independence?
So if you add any vector to this set, it's not going to be linearly independent anymore. Then you say it is a maximal linearly independent set. Any vector you add.
Yes.
Any vector you add to this linearly independent set.
Yes.
Once you add the vector, if the set becomes linearly dependent, then what? It becomes a linearly dependent set. Then you say that the set is maximal linearly independent. Take this one. You agree this is a linearly independent set?
Yes.
Now, suppose I add one more vector to it. Any vector. Now, is it linearly independent?
No.
No, ma'am.
No.
Is there anything special about this vector? I can add any other vector. Any x comma y. Right?
Ma'am, can you explain this by taking that question from Solve With Us week 4, question number 5 and 6?
Solve with us. it would have already been discussed in the session, right?
Yes, ma'am.
So you have a set with 4 elements. Can it be a basis for R2?
Basis for R2.
No.
What is the dimension of R2?
2.
Yeah. So first of all, this cannot be, the first option cannot be a basis. The set S itself cannot be a basis. The set in the first option cannot be a basis.
Ma'am, question 5 and 6.
Oh. Okay, fine. Which of the following sets are maximal linearly independent? Okay. Is the first option right?
Yes.
Is this max? No, why is it right?
Oh, no. No, last
you can
option
add a
is
vector to this. You can add a vector to the first set and still it can be linearly independent, right?
okay. Add a vector, still it linearly independent. Then last option, I think, right.
Yeah. Yeah. What about the second option?
No.
Scalar
It's not even linearly independent in the first place.
2 into 1 comma 2. That means the vector is scalar multiple.
This is not, first of all, for it to be a maximal linearly independent set, it has to be linearly independent. That itself is not happening, so it's not possible there. This is not right. But this one is maximal linearly independent, right? Because this is linearly independent, I cannot add any more vector.
No, cannot understand the point.
So, do you agree this is a linearly independent set? 1, 2, 1, 1?
If I solve it and if A and B are 0, then it is linearly independent.
Yeah.
And we find
so,
the determinant
if I add any other vector to this set, will it be linearly independent?
No, ma'am.
It cannot be, right? Because the maximum size of a linearly independent set in R2 is 2, right? Because the base can have at most 2 elements, right?
Yes.
Ma'am,
that is why the third. That is why this option is not right.
Ma'am, only one element also is independent, right? One element, but it is not an R2 space, but 1, 0, the first option, it is an independent, linearly independent set, although it is not in R2 space. So that is the reason we did not select this, right?
No, it is in R2. This is in R2. It is in R2, not because it means 2 components, yeah.
Yeah, ma'am, but it is linearly independent, no? It is independent because it is one element and it is independent. So, but we did not select this, right?
That's because it is not maximal linearly independent. You can still add one more vector and still make it linear.
Okay. Maximal.
Hello, ma'am. Ma'am, with that 1, 2 and 1, 1, we can't get the 0, 0, no, ma'am. So 0, 0 is in R square, or so that cannot be obtained from this, no, ma'am. So how can we say?
No, why can't? Why can't you? 0 times 1, 2 plus 0 times 1, 1.
Oh, okay. Okay.
You're allowed to do that. No?
Yeah, ma'am.
Hello, ma'am. I have a doubt in activity 4.3. Question number 7.
So in the same question, right, instead of 1, 1, if you had 3, 3 or 3, 4 or something like that,
anything is fine.
Okay.
Yeah. Ma'am, in this question
4.3. 4.3.
Oh, okay. 1 second. Yeah, this question. Let's solve this. In that question.
Third option 1, 2 and 1, 1. We can also check if it is linearly independent or not. We find the determinant is not 0.
Yes. Yes. Yeah. Okay. Activity 4.3.
5th and 7th.
Ma'am, on the previous question, can we also just do it like x into 1 by 2 plus y into, x into 1, 2 plus y into 1, 1 equal to 0, and thereby we can understand whether x and y are independent or dependent. Is that method also correct?
Yeah, you're saying this, right? You'll check
Yes.
whether x is equal to y is equal to 0. Yeah.
Yeah.
But when you have two vectors in R2, why do so much? Just find the determinant, no?
No, in general, I'm asking, ma'am, is this method correct too?
Yeah.
Okay.
Okay. Okay, question 7 in this activity. This is exactly what we discussed, right? We did 2 examples similar to this.
Ma'am, fifth number.
Which one?
The fifth one.
Sixth one, is it?
Yes, ma'am.
Okay, sixth one. Find the dimension of the vector space. This was discussed in that session, right?
Okay,
so see,
ma'am.
whenever you want to find the dimension of such vector spaces, first find the basis. And then once you get a basis, the number of elements in the basis will give you the dimension. This is also discussed in detail in this course, I guess. Or at least a similar problem.
If we slightly modify question number 7, if the equations are, if this is in R3 and equations given are x.
No, this is in R4. 4 variables are.
If it is in R3 means I have a similar question from last year papers. There it is in R3 and the two equations are given as x is equals to y and y is equals to z. And we have to find out dimension of that.
Okay.
So
you should be able to do it. We have already discussed.
Yeah, but I have a conceptual doubt in that. So x is equal to y and y is equal to z. In some of the session it is given number of non-zero row r is equal to equal to dimension number of non-zero rows. By that logic, if I solve, the
no, that's rank of a matrix, right? Rank of a matrix is the number of non-zero rows in the row echelon form.
Okay. For the vector, you have to see in
rank
number of
of a matrix is different from dimension. Yeah, dimension of a vector space. This is different. This is different. Dimension. So, sir has used the term rank also for vector space, but you ignore this. Just keep in mind dimension of a vector space and rank of a matrix. Okay, I guess we'll proceed. We are yet to discuss rank, right?
Ma'am, just one question. You just done that question on the span of UV is equal to span of VW. In that you proved that the span of UV was equal to the span of VW. And you said we check for the vice versa. Is it?
I have proved.
Yeah.
I proved. So I start with any element in span of UV. And what I have shown is that element belongs to span of VW.
Do we have to do the vice versa also?
Yeah,
this is sufficient
A is equal
proof.
to B. Two sets are equal if A is a subset of B and B is a subset of A.
Okay, so we have to do that.
Yeah. Okay, fine. So, yes.
Yeah.
So what is the answer, ma'am?
I have a doubt about the independent and dependent variable with respect to the reduced row echelon form. How can you determine which one is the dependent variable and which one is the independent?
So whenever there is a pivot in a column, the variable corresponding to that column is dependent. It was discussed earlier. Yeah.
Okay.
What is the answer, ma'am?
Okay, maybe
x comma x
for which
comma
one?
x.
What is the dimension? Tell me.
1.
Yeah. 1. There's only one free variable, right?
Yeah.
Everything, once x is fixed, you know what is y. And once you know y, z is also known. So there's only one free variable. And this will be a basis.
And 0, 0, 0 is also based. 0, 0, 0, 0, comma 0, comma 0, 1,
No. That's not a linearly independent set, right? This is not linearly independent.
Yeah. Okay.
Yeah. Okay, and what is span of this set? Span of this set is just 0, 0, 0. That's not the vector space, no?
Okay.
Okay. The last topic, we'll just quickly discuss this. What is rank?
of linearly independent rows.
Non-zero
So the
rows.
number of linearly independent columns in the matrix is rank. How you find this number of non-zero rows of row echelon form? So you just do the row echelon form of a matrix, and then the number of non-zero rows is the rank of the matrix. Yeah. So I think with this, all topics are covered.
Ma'am,
Do you have any
with respect to
doubts?
product of matrices, can you explain the rank?
Yeah.
Ma'am, is there any limitation that how much time we will process the row to get the non-zero? Is there any limitation or anything?
No. REF is fixed, right? Like, you know when you have reached a row echelon form, right? So after a finite number of steps, you will.
Unless until we get row echelon form, we just process the rows.
Upper triangular matrix.
Upper triangular matrix, unless until we get, we just process the rows.
Yeah, you convert it to row echelon form. That's it. Yeah. So what do we know about rank? Is rank of AB is equal to rank of BA. And then what else? The rank of AB is less than or equal to
rank of A or rank of B.
Ma'am, matrix multiplication is not commutative. That's why I think first option is not.
No. Rank of matrix multiplication is not commutative, but rank of AB is always equal to rank of BA. AB is not equal to BA, but ranks are equal for both the matrices.
After I multiply two matrices, then I process the rows and get the rank. This is the option.
Yeah.
First I multiple two matrices, then I get the rank. This is the way, na?
Yeah. Oh, wait. What did I say? No, this is not true. Is it necessary that rank of AB should be equal to rank of BA? No, right? AB can be a non-zero matrix and BA can be a zero matrix, right?
Yes, ma'am.
Yeah. Take some simple example. I think this will work. B is, say, AB. AB is 0, BA is
0, 0, 0, 1, ma'am.
Okay, then what do we get? What is AB? AB is 0, 1, 0, 0. What is BA? Yeah. So AB rank is 1.
1, BA 0.
Yeah. Rank of BA is, yeah. Sorry for that. But this is true. Rank of AB is less than or equal to rank of A, minimum of rank of A, comma rank of B. And rank of a matrix is less than or equal to minimum of number of rows, comma number of columns. Right? Means the rank cannot exceed the number of rows or number of columns.
Ma'am, last line I could not understand.
So if A is a 3 cross 4 matrix, the maximum rank it can have is 3. Minimum of number of rows and number of columns.
Okay.
Graded assignment 4, question number 1.
Graded assignment 4. Can you tell me the question? Because
Yeah, the first question with respect to the rank.
Okay. Okay.
Option 2 and 3, ma'am, can you explain that?
Rank of so we just discussed this, no? What is rank of AB? It's less than or equal to minimum of rank of A and rank of B. So rank of AB is less than or equal to rank of A and it is less than or equal to rank of B, right?
Ma'am, are there rules or something we should do on the exam? So how can we proceed to that kind of questions, ma'am? So we need to do by examples or?
So keep this in mind.
Okay,
With
okay, ma'am.
this, yeah.
So we need to keep that in mind and proceed.
Yeah.
Ma'am, it's supposed to be minimum of rank of A or B, right? Like whichever is minimum, that has to be the rank of A, B. So then the option number 2 and 3, it says less than or equal to rank of B.
Yeah. So the minimum of these two is less than or equal to rank of A. Agreed? Yes, right?
Yes.
And the minimum of this is also less than or equal to rank of B.
Okay.
And then maybe we'll quickly look at the mock paper and see if there's anything. The mock solutions will be uploaded, so you can check that as well.
Ma'am, can you tell activity question 4.3 7th question?
One second. Okay, that's that vector space thing, right? Dimension x, y, z, w.
No, ma'am, no, not that one. A equal to minus of A transpose, something like that.
Okay, one second. So in this third option, span of 1, 2, 1, 2, 1, 3, 0, 0, 2. Is that a vector space?
Yes, ma'am.
Yeah, because span of any set is a subspace. And now is it clear that the dimension of this statement 4 is 1?
Yes.
Yes, ma'am.
And then, so we've discussed everything.
Ma'am, I have a doubt in when element is 24, it is same.
Which
Last question. Last one. Yeah, this one. Minus of.
How will you do this? So you need to check how such matrices are going to look, right? So if I have A here, once I put the element here, is it fixed? What is any other element fixed? Oh, okay. What do I want? I want A to be equal to minus A transpose. So A, B, C, D, E, F, G, H, I should be equal to minus of A, B, C, D, E, F, G, H, I. Right?
Yes, ma'am.
What can you tell about A?
Fixed.
A should be equal to minus A.
A is 0.
Means A is equal to 0.
Okay. B should be equal to minus D. So I'll put minus D here. C should be equal to minus G. D should be equal to minus B, that I already know, right?
Yeah.
E should be 0 for the same reason, because E should be. So what F should be equal to minus H. So this is H. And this is G. So how many free variables here now?
3.
1, 2, 3, 4. 1,
2,
3.
So what is the basis?
Okay, 3. Okay.
3.
0,
3.
minus 1, 0, 1, 0, 0, 0, 0, 0. This is one of the elements in the basis. The next element is 0, 0, minus 1, 0, 0, 0, 1, 0, 0. And the last element is 0, 0, 0, 0, 0, minus 1, 1 second, 0, 1, 0. This is a basis.
Yes, ma'am. Thank you, ma'am.
I didn't get this 0 minus D minus G. Can you please explain it?
You want A to be equal to minus A transpose, right?
Right.
So if this is my matrix A, this is my minus A transpose. These two should be equal.
Correct.
A should be equal to minus A. When is that possible?
Yes.
Only when A is 0, right?
Correct.
B should be equal to minus D. So I'm just putting minus D there.
Okay. Right.
Yeah. And when I come here, D should be equal to minus B. That I already know. So I'm keeping D as it is.
Right.
Okay.
Got it, ma'am. Thank you so much.
Yeah. Yeah. So there was someone who had asked me about Gaussian elimination, right? Are you still there in the session?
Yeah. You can show with one example.
Even I would like to know more, a little bit more about that.
What do you want me to solve? Like solve a system of linear equations, is it?
Yes.
So say we have something like this.
You don't take a square matrix, ma'am. You take a rectangular.
Okay, fine. Fine?
Yeah.
So the matrix is 1, 1, minus 1. Augmented matrix I'm writing.
Yes.
2, 1, minus 1, 3. 1, minus 1, 2, 1. 0, 1, minus 1, 0. So I want to know whether the system has a unique solution, infinitely many solutions, or no solution. This is a random system, so I have no idea what it is going to be.
Okay.
So what is the first thing that we will do?
Row echelon.
What is the first? What is the first?
It has no solution because if I
This
solve,
pivot is fixed.
Ma'am, for 3 variable there is 4 equation.
from the equation 1 and the equation 2, right? Y1 is Z
Yeah, it has no solution.
X is equal
fine,
to 2x.
Okay, now let's see what it is. Even now it may not have a solution, but still let's try. Means our aim is to understand Gaussian elimination, right?
Yes.
Yeah. Okay. So now the pivot here is fixed. First row, first non-zero entry is this. Now I have to make all the entries below it to be 0.
Okay.
For that I will do row operations.
2R2 minus R1.
R2 minus 2R1.
2R1.
And then R3 is
minus
R3 minus R1. This is already 0, so no problem. 2 minus 2, 1 minus 2, minus 2 plus 2, 3 minus 4.
Minus 1.
1 minus 1, minus 1 minus 1 minus 2, 2 plus 1, 3, 1 minus 2 minus 1, 0, 1 minus 1, 0. Okay. Now my first row is done. Second row, I need to identify the pivot. Which is the pivot?
Minus 1.
This one.
Second row,
Zero
second
entry,
row.
leading non-zero entry. Yeah. I want my pivot to be 1. So I will multiply the second row with minus 1.
Minus 1.
Yes, ma'am.
Yeah. So this is 2, 0, 1, 0, 1, 0, minus 2, 3, minus 1, 0, 1, minus 1, 0. Okay. Now my pivot is fixed for the second row. I need to make all entries below the pivot to be 0. So for that, I need to make this entry 0. For that, I'll do R3 is R3 plus 2R2. And R4 is R4 minus R2. Zero, 1, 0, 1, 0, 0, 3 plus 0, 3, minus 1 plus 2, 1, 0, 0, minus 1, and then 0, minus 1. Okay, fine. And then?
No solution.
R3.
3.
I want to make this entry 1.
Yes, ma'am.
So I'll
R3
do
divided by 3.
R3 is R3 by 3. So 1, 1 minus 1, 2, 0, 1, 0, 1, 0, 0, 1, 1 by 3, 0, 0. I can make all these entries 0, right?
Yes, ma'am.
By doing one more row operation. Okay, let me do that. Oh, okay, I won't get 0. So R4 is R4 plus R3. 1, 1, minus 1, 2, 0, 1, 0, 1, 0, 0, 1, 1 by 3, 0, 0, 0, minus 2 by 3. So no solution, right?
Yes.
Yes, no solution.
Suppose this entry was 0, then
This one.
Many solutions.
Unique solution.
Infinitely many solutions.
Unique solution, no?
Unique
solution.
No,
Unique solution.
infinitely many solutions.
Each of the 3 rows has
No. Many
No,
solutions.
no. See, there is a pivot in each column. So you will have a unique solution. No independent variables, right?
Okay.
Yeah.
But in the first row, there is a 1, 1, minus 1.
So what? Suppose this entry was 0. Okay. Let's assume this entry is 0. So now my system has reduced to x plus y minus z is equal to 2. Y plus z, y z is 0. So this is 1. Z is equal to 1 by 3. So just substitute these two, you will get the value of unique solution. So there is an independent variable, means there is no independent variable.
Then it is infinitely many.
No, unique solution. If there was an independent variable, then we would have had infinitely many solutions.
Because it is 3 variable and 4 one equation. That's right.
Yeah.
And ma'am, what is rank of this argument?
When it will be the no solution, ma'am?
What is it?
Some constant.
When it will be the no solution?
No, here no solution came, no, minus 2 by 3.
The original problem that we had has no solution.
The rank of this is 2. If it is not 2.
Rank of?
Rank
No,
of
rank
this
of the augmented matrix is 4, right? Augmented matrix is 4 because this is non-zero. Originally, this is non-zero.
If it is not 2 by 3, then it will be 3.
1, 1 minus 1, 2, 0, 1, 0, 1, 0, 0, 1, 1 by 3, 0, 0, 0, 0, then it is 3. Here the rank is 3. Here the rank is 4.
And from the original equation, if we want to see the vector dimension, these 3 equations, what you have written, what will be the dimension of these 4 vectors?
No, if I put these 4 conditions together, it's not even going to be a vector space, no, because 0, 0, 0 does not belong to.
Okay.
Actually, what is the main difference between Gauss elimination method and reduced to row echelon method? Both are same.
No, see, you do row echelon form.
No, reduced row echelon form.
In reduced row echelon form, you want to make these entries also 0. So this is a pivot. Okay.
Lower triangular matrix also will become 0.
So, ma'am, for Gaussian elimination, we don't have to make it reduced row echelon form, right?
No. Even with this row echelon form, you can.
And does this apply also for checking linear dependence and independence?
Okay.
For even
the number of non-zero rows in row echelon form is enough.
Okay.
Ma'am, here the rank is 3 because non-zero rows are here 3 rows, but they are in the in augmented matrix. What did you say? Why the rank will be 4 there? Because that is also 0.
This entry is non-zero, no? No. Originally it is not 0. I said if it is 0, what had happened?
Okay.
And okay, now row echelon form and Gauss elimination method, what is the difference then? Row echelon form also we are making upper triangular matrix 0, and Gauss elimination.
No. See, row echelon form is you are converting a matrix into one form. Gaussian elimination is you are converting it into a row echelon form and solving the system. That's it.
Oh, okay. That augmented matrix will come in Gauss.
Yeah, you're solving the system of linear equations using Gauss elimination, in which you're doing this row echelon form and all that.
Okay.
Ma'am, what is the difference we can say between the rank and dimension, ma'am? Both look very similar.
No, rank and dimension of what? Rank is of a matrix and dimension is of a vector space.
Okay.
Yes, sir has also mentioned rank of a vector space, but let's stick to dimension of a vector space. Rank is defined for a matrix.
This would, if this was -2/3 at the end, would this be considered as a zero row or non-zero row?
No solution. Means
which one?
No, for a rank of a matrix. For rank of a matrix.
For the rank of a matrix, this is a non-zero entry. So rank is 4. Number
rank
of
is 4.
non-zero
Okay.
rows is 1, 2, 3, 4. Yeah.
Okay, and if we were checking the dimension, then in that case we would have this as a homogeneous system, and all, you know, to the right would be all zeros, and then we can just count the number of independent variables as being, I suppose, 2.
Can you repeat?
So the base, if supposing based on this we were supposed to find the dimension of the vector space. So
Okay.
so
No,
I
see,
suppose the right hand side would have
first
to be
of all,
all zeros.
This is not going to give away. Okay.
Yeah, and then we can just from there, if all the to the right would have been all zeros, then we could just simply count the number of independent variables, and that would give us the dimension.
Yes, yes. That's what is the number of free variables which we were talking about earlier.
Yes, but for that, to the right, it would have to be 0. That means it
All
would have to be a
zeros.
homogeneous system, right?
Yeah.
Just a request. Is there a possibility to have only for week 3 and 4 and more on week 4 on Saturday after the regular session? Because
no, there's no regular session on Saturday, right?
Okay, then can we have a special session for 3 and 4? Is that possible? Means you can discuss internally, but this is just a request.
No, but why? You already have detailed contents have been discussed in the earlier live sessions, and
I fully agree that one. There are a lot of.
It's a request. It's a request. If it is possible, then yes. If not, then
means we will go with the video. But the reason is, to be honest, week 4, many people, at least I couldn't spend time. So today, tomorrow, day after tomorrow, we will be concentrating on those videos. And once we go into the videos, we will get some doubts. That's it.
Okay, Shubhajit,
at least 1 hour session. 1 hour session, at least. Quick, only we can focus on 3 and 4. If
so, there is a request. What do you say?
Actually, I think he has messaged in the chat also, right?
Yes. I only messaged. Yes.
Yeah. So I was suggesting you to go through the previous live session.
No. I fully will follow that. But once we go with all these things, then finally we won't have any other session to clarify other than discourse forum.
But I mean, do you want us to take a session on Saturday, because Sunday is your exam? So
it will be effective, sir, if it was on Saturday.
But should not you just focus on your learning on Saturday?
Yeah. Only revisions you are telling. Okay.
Only the day before the exam, no? So it would be helpful if you just focus on that day. On your own
learning. Okay.
We'll be super
if
active
you
on
still
Discourse,
have a doubt
so you
tomorrow, can you write in Discourse tomorrow?
Yeah, okay, fine.
Okay, so you just
we will be active on Discourse. Yeah. So.
Ma'am, when do you upload the mock test solution?
It is uploaded.
But one thing, thanks for your patience. Okay, thank you.
Oh, to me, thank you. It's okay.
Yeah.
Thank you, guys. Thank you, both of you. You guys are taking enough efforts to ensure that all of us understand it.
Yeah. Actually, you people are very dedicated. Thank you.
Thank you.
Ma'am,
Good night and all the best for the.
Ma'am, can I ask a question?
Thank you, ma'am.
Yeah, sure. Please go ahead, ask the question.
Yes, ma'am. 4.4 activity question 10, if you can.
One second.
Ma'am, it is about minimum possible value for rank of AB. Rank of A is given and B is given. Yeah, so randomly I am able to do it, but you know, I am not able to prove it or get the general sense of it.
So the rank of A is 3 and the rank of B is 2. Minimum possible value.
I think 2, no, madam. Minimum of A and B.
No, the maximum possible value is the maximum possible value is 2. The minimum. Maybe you can ignore this for now. You can ignore this for now. Once you study week 5 content, it's straightforward why the minimum possible value will also be 2. You can ignore this for now.
Okay, by rank nullity theorem.
Yeah.
Otherwise, we can't do without rank nullity.
You can do, but it's a roundabout way. Using rank nullity theorem, it's straightforward.
It's not needed for now. Can we say that?
Yeah.
Sure, ma'am. Thank you so much, ma'am.
You can focus on maximum possible value for rank because that is straightforward.
Yeah, that is straightforward. Okay, ma'am. Thank you so much. It was a beautiful session.
Yeah, thank you.
Hello, ma'am.
Yes.
Ma'am, last question, ma'am.
Yes.
Ma'am, sir have explained video last, I think 4 points something. We can find rank and dimension of every vectors using Gaussian elimination method. Taking vector as a column of matrix and leading column, leading entry column indicates rank, and number of leading entry column is a basis of that vector. Can we use this concept for all vectors and matrix?
No, the leading entry, the column corresponding to leading entry is what? Can you repeat that?
Column corresponding to leading entry is basis of that the vector space.
Yeah, you take the pivots. Wherever you have a pivot, you take those columns that will form a basis. Okay, fine. Then.
Yeah. And the number of dependent variable is dimension of that vector space.
The number of independent variables.
Dependent variables. Dependent variables.
No, the dimension will be the number of independent variables.
But
because only when you have independent variables, we discussed that spanning thing, no? X1 times some vector plus X2 times some vector.
But
those were because they were independent variables.
I think a leading entry column is a dependent variable, madam.
Whenever you have a leading entry, it is dependent variable.
Dependent variable. So number of such column is dimension or rank of that particular vector space. Sir have explained in video, madam. I don't know. I am not understanding why such thing is happening.
Ma'am, when we talk about rank, that time it will become independent, right?
When we talk about rank,
it becomes.
Can we go through that video, madam? Can we go through this video? I think video is.
When we are talking of pivot, that time we say it is a dependent variable.
Yeah.
And when we talk of rank, we say.
Which video? 4.4 is it? Which video is that? Santosh sir asked the question, right?
Ma'am, meanwhile, can I ask a doubt from lecture?
4.4, madam. 4.4.
Okay, 4.4. What
4.
time?
Yeah. 4.4. Rank and dimension using Gaussian elimination. Sir, I have explained two methods, madam. Taking vector as a row and taking vector as a column. Okay, madam. Taking vector as a row and taking vector as a column. So, sir, I have explained taking vector as a column. This thing, I think, leading entry column.
Leading entry. Okay, here, so you take it in. Rows and
Next. Yeah. Yeah. Next.
Can we get a basis constant? Okay, fine. And then?
Next, madam. Next.
This one is what you're saying, right? If R is the matrix obtained by row reducing A, then the columns of A corresponding to the columns of R containing pivot. Yeah, so
that is, I am saying, that is dependent variable, I think. That is column.
Yeah, the columns corresponding. Wherever you have a pivot, those columns will, corresponding
That will be independent variable, no?
No, that is dependent. That is dependent. Column containing pivot element is dependent variable.
No. If we, after reducing,
columns containing pivot is dependent variable, but don't confuse that with this.
And after reducing, if we have some pivot, so that means that it is independent, no?
No, it's dependent. No, when you have a pivot, it's dependent. Here it's written, no, that is the leading ones or equivalently the columns corresponding to the dependent variable.
Yeah. I think I'm confused with something else.
Now, if the session is over, we can leave now.
Sure.
Okay, thank you very much. Thanks.
But when we find the rank, that time we say it is an independent variable, right?
Yeah, the number of non-zero rows. The number of linearly independent columns or rows in the matrix.
Okay. But here is something different, I think. So I am very confused after that. And sir is saying this is a versatile method. You can use anywhere this method to find.
You can actually.
This is a very.
You understood how to find the basis, right?
Yeah. I got. Yeah.
So, at least for the current, for the sake of quiz, it is clear.
Yeah, that way we understood.
Okay, madam.
Thank you, ma'am.
Ma'am, can I ask a doubt from lecture?
Good night, ma'am.
Yeah, sure.
Thank you, ma'am.
Thank you. Yes, Ayush.
Yes, ma'am. It was from lecture 2.3.
Okay. Lecture 2.3.
Ma'am, I think somewhere around 20 minutes.
Okay. What is the doubt?
Sir was calculating some or deriving some formula. I am not able to get it. The steps of. Yeah, exactly.
This one is it?
Yeah.
This I have explained this on Discourse. You can check there. There's exactly the same thing. This is exactly the same.
It will be the same thing, but I am not able to get it how it is.
I have explained it line by line on Discourse. Maybe you can check there.
Okay, ma'am. Sure. Okay, ma'am. Thank you so much.
Thank you.
Now it's done. Good night, ma'am.
Good night.
Thank you very much, ma'am. Good night.
Good night. All the best for the quiz.
Thank you.
Thank you, ma'am. Thank you.